antioxidant towards almost all noxious intracellular reactive oxygen species. Also a fascinating material for biomedicine, drug delivery, and bioscaffolding. Coming to general applications, cosmetics, because it's biocompatible, so the lot of applications for Syria in cosmetics. Also gas sensors, ceramic biomaterials, solid state electrolytes, chromatic materials, oxygen permeation membrane systems. So you can imagine how important cerium oxide is in the area of catalysis. So why it is so important? Why it is showing the exceptional properties? So you can see the outer electron configuration is something like 4f1, 5d1, 6s2. So this exhibits 4 plus 3 plus oxidation states with very small energy variation. So this is a rapid, basically 4 plus to 3, 3 plus to 4 is very rapid. So because of this, what you call intrinsic property, this has been exploited in various fields. So this also very interesting. Actually, these are classical uses of cerium oxide include pyrophoric mesh metal alloys, especially in cigarette lighters, but also cerium 3 oxide in self-cleaning ovens. If there is a coke for it oxidizes and prevents the coke formation, the self-cleaning. But also in the film industry, especially for the projector and studio lighting. And cerium oxide has been called as an industrial vitamin and a treasury of new materials owing to numerous applications. This is very interesting about the cerium oxide. Although it is labeled as a rare earth, but it's not exactly rare earth. It is a 25th most abundant element on Earth's crust. Apart from China, Brazil, USA, we do have a lot of these minerals, cerium containing minerals that include alunite, monazite, and cerite. So these are the two intrinsic features of cerium: a fissile cerium 4 plus 3 plus redox couple, and a high oxygen transport capacity from bulk to surface to bulk, basically. So under reducing atmosphere, like hydrocarbons, hydrogen, or CO, loses considerable quantities of oxygen, forms oxygen vacancies. When exposed to oxygen environment, so reoxidizes, comes back into original state. So this is the beauty of this, like sponge-like material. As you are aware, where you put the sponge in water, it keeps some water. When you press, the water comes out, but there's no structural collapse of the sponge. So cerium oxide also acts like a sponge with respect to oxygen. It gives oxygen, takes oxygen. So because of this inherent or silent feature, intrinsic feature, cerium has been exploited in various fields of chemistry, biology, and physics. But however, it has got disadvantage when we talk about catalysis. Normally, catalytic reactions we do at higher temperatures, but at higher temperatures it loses its thermal resistance. Is that if you go more than 300 degrees centigrade, it loses thermal resistance, low thermal resistance, because its structure will be collapsed, and so thereby it loses its crucial oxygen storage capacity. So there are various ways to overcome this problem. So that was our theme of work, basically. That was actually, as I mentioned in the previous slides, that how Syria is important in various domains. So this was something like 20 years back. So this was when we started. Then the thought was how to enhance the efficiency of Syria, because we have shown that Syria is a very interesting metal oxide or rare earth oxide in the area of catalysis. But we are not happy with the efficiency of Syria and how to enhance its efficiency. So that was a question raised that come to our mind. So that led to the work actually the last 15-20 years. So these are two ways we can enhance its efficiency. One is the size reduction. So when you reduce the size, we need a support to stabilize it for ultimate catalytic applications, and incorporation of dopants, basically. If there are appropriate dopant in the serial structure, so we can enhance its efficiency. So there are two ways we can think of enhancing its efficiency. When you think of size reduction, those who are not familiar with the concept of nano, this is a very good example. The bulk gold looks yellow, but whereas nano, 12 nanometers of gold looks red actually. So this is there's a change in the color when the size change in the size, basically. It is also experimental observation. This report was available in 2011 in Journal of Physical Chemistry. So melting point of gold, when the particle radius is 10, for example, the melting point of gold is 1060. So if you reduce the particle size to 2 nanometers, melting point of gold is 500. Almost 50% reduction from 10 to 2 nanometer size. So So when you reduce the size from 10 to 2 nanometers, so the melting point is from 1060 to reach to 500 degrees, 50% reduction in the melting point actually. So that's why the concept of nano revolutionizes our understanding, and we are all even asked to change the old books basically. The melting point, boiling point, these are the definite properties, but this the concept of nano is proved that these are not the definite things basically. So this needs no explanation. So 1 meter cube, so the exposed area 6 square meters. So when you need to make it 4 pieces, 12 square meters. When you make into 27 pieces, it's 18 square meter surface area. In other words, when you go too small, you can get more exposed area. So that is the concept of nano. So nano, as per the definition, the structures with at least one dimension between 1 and 100 nanometers is called nanomaterial. So as per the definition, all these like nanospheres, cubes, fibers, spindles, all these are nano because as per the definition, it is one dimension. So nanotechnology is nothing but application of nanomaterials into useful nanoscale devices. Now, as I mentioned, the nano influences all these properties. As I showed in the previous slide, there's a change in the melting point. So nano sizing influences all these properties: color, conductivity, magnetism, light absorptivity, crystal structure, chemical reactivity, melting point, and boiling point. All these physical properties change with the size change. So coming to catalysis, when the particle size is less than 100 nanometers, there's as per the definition of nano, materials become nanophasic, density of defects increase. So almost 50% atoms will be in the course of defects. That includes like grain boundaries, interface boundaries, and dislocations. So all these enhance the catalytic activity. So as high density defects provide a large number of active sites for gas solid catalysis. Therefore, we can expect better activity when you go from conventional to nano. Yes, we can make the nano as we have shown that. So those who are not familiar with the TEM picture, so always the TEM picture will be a small scale. So from here to here 2 nanometers. So this is a 6 nanometers of ceria oxide nanoparticles. Even treated at 600 degrees, they are quite stable. As we have shown, we can make the nano. Not only ceria, and also we have shown that we can make the variety of materials with like ceria zirconia, cerium lanthanum, cerium samarium, and cerium iron. All these mixed rocks are solid solutions we can make in the nano range basically. But also in the ceria and silica, because as I mentioned, when you make a nano, so we have to stabilize it. What for ultimate catalytic applications, because the catalysis normally takes place at higher temperatures. So to stabilize it, we need an appropriate support. So in this case, we took the silica. Here, the 4 nanometers from silica, ceria and silica. Even if treated at 800 degrees centigrade, it's quite stable. So this is a very good catalyst for variety of reactions. Here we have shown that ceria zircon and TiO2, the TiO2 anatase is a 40 nanometers TiO2 anatase on this ceria zirconia. So this is the expanded form. So in other words, yes, we can make ceria, not only ceria and ceria based or incorporated dopants in the ceria structure, and we can make it to nano, and also we can stabilize and appropriate support to make use of these materials for catalytic applications. Now the next option is a incorporation dopants. So there's a 2 ways we can incorporate dopants in the ceria structure. Substitution of isovalent cations, because ceria exhibits 4+ oxidation state. So we can put like a 4+ oxidation state elements like the zirconium or this intrinsic mechanism. Through this, it show the better oxygen storage capacity and very good reactivity. And also the cerium shows 3+ oxidation state. We can also incorporate aliovalent cations like lanthanum 3+, terbium, residumium. So these type of dopants we can into the ceria structure, and this mechanism is slightly different, charge compensation mechanism. So by both ways we can incorporate the dopants in the ceria structure, and we can enhance its efficiency. So that was the ultimate goal basically. As I mentioned, when you incorporate these things, we need these incorporated materials in the nano size. When you talk about nano, we need an appropriate support to stabilize them for ultimate catalytic applications. Now the choice of dopant is a big question mark. So there are a lot of theoretical studies also available in the literature. So all these are yellow marked elements. All these are theoretically we can use them as a dopants to incorporate the ceria structure. But there is a small difference basically, like based on these theoretical studies and based on ionic radius, If the cerium 4 plus ionic radius bigger than cerium 4 plus ionic radius, like thorium, is not a good dopant. But on the other hand, cerium 4 plus ionic radius smaller than cerium 4 plus, like titanium, hafnium, zirconium, these are the very good dopants. So as per the theoretical studies, titanium is a very good dopant in the Sierra structure, but it is very difficult to make titanium incorporated Sierra through normal precipitation methods. We have to use a different method, like what you call combustion synthesis or microwave assisted combustion synthesis and synthesis, like basically there the chemist role comes basically. Now, what is the evidence? Basically, I mentioned when you put in dopant in the Sierra structure, there is a enhancement, the reduction. So this is evidence from TPR basically, that the pure Syria, when you do the TPR, so this it exhibits two peaks, like low temperature reduction peak and high temperature reduction peak. So this pure Syria only 30% reducible Syria. So if you incorporate zirconia into the Syria structure, we can go for 40 to 80% reducible cerium. So this is the Syria zirconia, same under identical conditions TPR. So we can use, this is characterized by only one peak. It's slightly different, lower temperature than the high temperature redox, what you call a peak in pure Syria. So in other words, we can go, when you put the dopant, appropriate dopant, we can go to higher reducible cerium. So higher reducibility means more reactivity. So this is good evidence from TPR. And also we got good evidence from exhaust measurements. These measurements we have carried out in Germany. It's a Hamburg synchrotron radiation facility. So here the simple logic is cerium 4 plus a model compound like cerium oxide exhibits two peaks, and whereas cerium 3 plus model compound shows only one peak. So this is, we have done the in situ reduction experiments to start with room temperature. So mostly Syria zirconia in a cerium 4 plus oxidation state. So we reduced it with CO, because CO is a mild reducing agent, and started increasing the temperature under CO atmosphere. So go on, increasing the temperature from room temperature to 550 degrees centigrade. You can see from cerium 4 plus is become cerium 3 plus. So as I showed here, the cerium 4 plus exhibit two peaks, cerium 3 plus only one peak. But here also you can see the cerium 4 plus is becoming cerium 3 plus when go on increasing from room temperature to 550 degrees centigrade. So this is a good evidence from this, and we can go number of cycles. After completing the 550, you can stop again, restart. The same the way we get the same type of peaks we get basically. So that shows a very good, what you call no, there's no structural collapse. This is like a sponge-like material. So this can be used for various critical applications. Most importantly, at auto exhaust purification as an oxygen storage material. Because of this inherent property, this has been exploited for auto exhaust purification applications. Then come to the examples. As I mentioned, I'll show 5 examples. Auto exhaust. So transportation sector almost contributes 40%, 46% pollution to the environment, followed by aviation 29%, industrial 16%, solid waste 2%, and others 7%. You can see how much transportation sector contributes to the pollution. So this again small variation between the petrol engine and diesel engine. Petrol engines emit at least three pollutants: unburned hydrocarbon, NOx, and CO. Whereas the diesel engines add two more: sulfur dioxide and particulate matter. So it's all known that the hemoglobin transport the oxygen to the cell of body, every cell of the body. If there is CO, it forms a carboxyhemoglobin and stops the oxygen transport. So if CO concentration is something like 0.16 percentage, death in less than 2 hours. If it is 1.28%, death in less than 3 minutes. You can see how how bad the CO basically. Thanks to the auto exhaust purification technology, this started 1976 to start with two-way catalysts to take care of the unburned hydrocarbons, and then the oxidation of CO. Then came the three-way catalyst, which includes the reduction of NOx, because this is very tough. Basically, reduction of NOx under oxidizing atmosphere. That's what we need in a noble metal or combination of noble metals basically. Now we are talking about the four-way catalyst that includes the oxidation of soot basically. So this, this started in 1976. And you can imagine every vehicle is fitted with the catalyst, the three-way catalyst, or auto exhaust purification catalyst or critical converter. So this is the beauty of the what you call the importance of the cerium in what you call in environmental pollution control. So 40 years of catalysis by Syria, a success story, because there is a small group spread throughout the world. Actually, I'm also part of that group, exclusive working on Syria. So therefore, we celebrated 40 years of catalysis by Syria, a success story with a special issue in applied catalysis B. So because this 2016, exactly after 40 years, we celebrated. So this to start with the cerium, then came the Syria zirconia. Now we're working still better materials basically. Now the earlier because the three-way and the four-way now the suit has become very important. Actually, is tough to what you call a control. Of course, there are various ways like diesel particulate filter, and also whether we were to incorporate this before the three-way catalyst or after the three-way catalyst, because they're highly proprietary, because each automobile or car making companies use their own proprietary technology. So but of course this is very serious problem. And also where the cerium acts as a very good what you call active component in the diesel particulate filter technology. It oxidizes when there is a soot basically into CO2. And also cerium pure or nano ceria is also additive to a diesel basically. If you add nano ceria in 10 ppm level, so that takes care of the soot formation. Whenever there is soot, automatically oxidizes into CO2. Now coming to the as I mentioned, we started so about nearly 20 years back. So with the simple Syria, then came out with Syria zirconia, because Syria zirconia is a commercial practice material for auto what you call oxygen storage and release property. And we thought, because of zirconium and hafnium shows similar properties. In fact, very difficult to separate hafnium from zirconia. Why not we use the hafnium? So that was with a simple idea. We prepared the hafnium incorporated Syria, and we studied the CO conversion, CO oxidation activity. To our surprise, we got excellent results. Basically, same conversion at 120 degrees less temperature. They call as a light of temperature. Temperature required for 50% conversion is called light of temperature. Based on this light of temperature, also we can compare the different catalysts, which is a very active. Basically, the otherwise normal way is to calculate the activation energy, but it's a time-taking process. But this is the simplest way to compare a different catalyst, and based on this light of temperature, we can say which catalyst is the best one, which catalyst is very active. So you can see the same conversion at 120 degrees less temperature. So then we thought, why it is showing the such a excellent activity. Then we got from characterization studies that OSC, oxygen storage capacity, Syria often shows slightly better oxygen storage capacity than Syria zirconia. And from XRD measurements, we did not find any big difference between the cerium hafnium, cerium zirconia, but we got an excellent information from TPR basically. So Syria zirconia exhibits two peaks: low temperature reduction peak and high temperature reduction peaks. And on the other hand, cerium hafnium also exhibits two peaks, but at much lower temperature. So that means this is the cerium hafnium is more reactive than the Syria zirconia. So we did not realize the importance of these results. Basically, we just sent in a letter to Journal of Physical Chemistry. This came in print in 2 weeks actually. So after seeing this paper, and immediately the Nissan from Japan, actually they contacted us, because they came all the way to our institute, and because they are looking for a better material than Syria zirconia, especially to take care of cold start emissions, because whatever the technology is available, so these catalyzers start working only after reaching certain temperature. Now their goal is to look for a better material so that they can take care of the cold start emission. The moment you start the vehicle, the catalyzer starts working basically. So for that purpose, they wanted to exploit this material. We signed agreement and we worked with them for 3 years basically. As I mentioned, hafnium is isovalent, because like zirconium, it shows 4+ oxidation state. Terbium is a different actually, allovalent cation, it shows 3+2+ basically. So this we found that even terbium also very good dopant in the Syria structure, and also exhibits much better activity than the conventional Syria zirconia. And also cerium lanthanum actually. So this TiO2, you all know that TiO2 is a very good photo catalyst. So we wanted to develop some catalyst for VOC oxidation, volatile organic compounds oxidation at room temperature. And this catalyst was found to be very good even at room temperature for oxidation of ppm levels of benzene or toluene at room temperature to convert it to water and CO2. And this was also found to be very good for CO oxidation. And samarium, this is another allovalent cation dopant into the Syria structure, and we thoroughly investigated. This was also found to be another very good dopant. Manganese among various dopants, manganese was found to be the excellent dopant compared to other dopants. So this we thoroughly characterized and also published these results. So among various dopants, we just made a comparison. Among various dopants, manganese was found to be the best actually. So then came the like hafnium, praseodymium, lanthanum, all these dopants basically for both CO oxidation as well as soot oxidation. Then why not actually when you have the one dopant, put two dopants basically with the same concentration, because so to decrease one of the dopants concentration, I do add then equivalent to second dopant. To our surprise, we can still get the better better activity. In other words, the activity at much lower temperature. So this concept also worked very well basically. Now these were up to this we only concentrated the size, nano size basically. So this play, the plane also plays major role basically. We call so nanocubes actually. When you make, and in fact, the Erittel got Nobel Prize for ammonia synthesis catalyst because he showed that iron 1,1 plane is more active than other planes. For that, he got the Nobel Prize basically. And we have shown that we got a very surprising results that not only size, also the morphology plays a major role in CO and soot oxidation. And nano manganese cubes basically. I don't want to go into details, just want to give a flavor of this information so that those who are interested to go into this area, they can work basically. Nano wires basically. So not only size actually, the morphology plays major role, like cubes or wires. So when you make, you can get still better activity. So this is the story about, and they're never ending because we have some more papers. So I will stop that example. Now go to the next example, mercury abatement. So this Minamata Convention until 19 January 2013, so mercury emission was relatively neglected. On 19th January 2013, almost 140 countries under UNEP signed an agreement. Now, as per this agreement is called as the Minamata Convention. So we cannot just like that emit the mercury into the atmosphere, because the pink disease is more prevalent in Korea, Japan, and China. So this especially the babies are hypersensitive to the mercury. We call pink disease. So this also Minamata disease, because Minamata is a small bay town in Japan where almost 27 tons of mercury compounds were dumped actually. So during this period, so this resulted in the form of a typical disease called as Minamata disease. The trouble in walking, numbness, and convulsions and death actually. So based on this, they called as a Minamata disease, and also Minamata Convention under UNEP to control the mercury exposure basically. How the mercury comes into the atmosphere. So these are the three culprits basically. Coal-fired power plants. So this is the main culprit to emit the mercury to the atmosphere. Then comes the chloralkali industry. Then volcanoes, because of course we don't have control on volcanoes. So we have to bear this basically. So this is very interesting information. And coal contains up to 0.1 to 0.15 milligrams of mercury per kilo of coal basically. And concentration of mercury in the flue gas ranges between 1 to 20 grams per cubic meter. So as per because we wrote an excellent review on this subject basically, the power plant capacity of 775 megawatts power plant capacity emits 2.3 kilos of mercury per day. You can imagine basically, we always talk about what is the capacity of power plant actually, 1000 megawatt, 2000 megawatts. So in that process is how much? 2.3 kilos of mercury per day. So this is how the mercury goes into the food chain. So mercury is emitted to the atmosphere. Mercury is deposited in the rain and snow. So mercury accumulates in lakes and reservoirs and forests. The mercury is transported through watersheds and converted into methyl mercury. So methyl mercury is a neurotoxin, and so with methyl mercury bioaccumulates in food webs, especially if we eat the fish contaminated with methyl mercury, and we end up with this mercury, what you call Minamata disease, or the typical disease basically. And if you see the literature, so coal consumption, almost United States 50% of energy comes from coal. China, two new 500 megawatts power plants every week. India, more than 50% energy come derived from coal. And China, India, 60% of demand in the world coal through 2030. And not only from mercury, and also other emittents like, of course, greenhouse gas, sulfur dioxide, toxic metals such as cadmium, gallium, arsenic, selenium, apart from mercury. So when you see the information available, even 2035 also coal is going to dominate in the energy sector. So what are the technologies available to, and about the mercury, there are three species like elemental mercury. This is the main culprit. 94% of total mercury is in the atmosphere. It is water insoluble, long atmospheric life form, 6 months to 1 year basically, and globally distributed. So if one country emits produce mercury, it will be spread to other countries. There is a part of mercury oxide is mercury because coal also contains small amount of chlorine. This is in the mercury chloride basically. So highly water soluble and more local and regional because this is not a big headache basically. And also particle bound mercury because mercury also attached to the ash basically. When you burn coal basically, there are a few percent of mercury is but this what you call this is highly localized and this atmosphere life is of 1 to 2 weeks basically. So what are the technologies available to take care of the mercury? There are key major technologies available. Actually, these are two major technologies are available. Actually, these are practiced. So this includes electrostatic precipitation and also fabric filter and wet fluid gas desulfuration. So these are the called air pollution control devices, APCDs, and also sorbent injection. Basically, by injecting an activated carbon, so through the system, so this are activated carbon forms amalgamation, absorption, so takes some mercury. But the biggest drawback with this technology is because activated carbon is expensive and environment problem going to disposal, because where to dispose the used activated carbon. And because of these reasons, although these technologies are practiced, there's a need to have a better technology. And we have seen actually from the literature that the best technology can be catalytic oxidation. If you oxidize the elemental mercury in the system, so we can take care of it, especially to converting mercury, elemental mercury to mercury replace or mercury chloride or mercury other compounds. So we can get rid of this through wet fluid gas desulfuration. By scrubbing, we can take care of this one. So this we came out with a review article, and also because we have shown that our catalysts like cerium-based catalysts that we have developed for different purpose, and for this exclusive purpose also found to be very good catalyst, very good active catalyst for elemental mercury oxidation, even at much lower temperature, about 180 degrees to less than 200 degrees centigrade. BHEL R&D showed interest on this because BHEL makes this equipment, the electricity generation or thermal power plants equipment exports to Gulf countries and African continent. So they showed interest on this technology. So this is a typical, because it's very difficult to study the mercury, elemental mercury oxidation in the lab. This is, in a few mode, these experiments were carried out in, they collaborated in Australia. This is a typical experimental setup to carry out the elemental mercury oxidation, because we have to generate mercury vapors and oxidize it. Uh, as I mentioned, because we are working on the more superactive cerium-based catalyst, and we found that cerium lanthanum and cerium manganese combination exhibit very good activity for elemental mercury oxidation. We also thoroughly investigated elemental mercury oxidation with chlorine or without chlorine, and also added another promoter like iron into the system, and we investigated thoroughly. Yeah, that's actually, there's still work is going on. I don't want to go into the details. So I'll stop here, and then next example is a toxic chemicals abatement. So this is some sort of secret project. Actually, we work for the DRDO organization. So to take care of the warfare chemicals, especially the battle tanks and the aircraft go into the battlefield. So they need some sort of what you call a small equipment to what you call neutralize the warfare chemicals while drawing air into the what you call battle tanks and the aircraft. That was a thing. So then because we studied some of these narrow agents, the chemical warfare agents include all these basically. These are the structures of these compounds, and we have studied some of these model compounds too. And we came out with the system basically. So this is can be fitted in the battle tanks or also in the aircraft, so when they go into the war zone. I transfer this technology to DRDO. Now the next example is the carbon dioxide utilization. We already heard very good information from Professor G.D. Yadav talk. So this is a continuous increase of CO2 in the atmosphere, and there is a direct relation between the temperature rise and CO2 concentration. As of July 2011, concentration of CO2 in the atmosphere is 392 ppm. So as of April 17, actually April 17 2022, 420.87, almost 29-30 ppm increase in 10 years. So what are the other options available to address the CO2? Prevention of CO2, avoiding formation of CO2. This is the best option, but we can't avoid in certain things, but it can minimize it. At the commercial use of CO2, all as chemists we always like this to utilize CO2 to make chemicals or very more important products. And disposal of CO2, the CO2 sequestration, this is also very good option. But again, is a big question mark. If you store in the dead oil wells or underneath the sea, but what happens after 100 years or 200 years, nobody knows basically. So CO2 can be used in various ways. Only carbon part of it can be used to make fuels. Oxygen part of CO2 can be used to alcohols, epoxides, and CO2 itself can be used to make carbonates, carbamates. CO2 is an oxidant actually. This is some sort of new concept actually. CO2 is a soft oxidant. So we have done a lot of work on this. CO2 is a soft oxidant. So this is the commercially practiced methyl benzene to styrene, oxidative dehydrogenation of methyl benzene to styrene. This is commercially practiced technology. It's almost 100 years old technology. So this is practiced at at 650 to 700 degrees centigrade, and equilibrium conversion only 60%. The same can be done using instead of using CO2 as soft oxidant at 100 degrees less temperature, and 10% more conversion. Equilibrium conversion only 60% here. Here can go up to 70% conversion. And another important observation is the CO. CO is a product, byproduct. You all know CO is the most valuable product compared to CO2. So this is less temperature, more conversion, and CO is byproduct, valuable byproduct. So this we have done actually a lot of work, and also come to pilot level. This with the support from SOBIC. Because CO is a better dilute, gaseous nature, prevents hot spots in the reactor. Those engineering people know that what is hot spot. And mild oxidant and catalyst life booster. Whenever there is a coke and it oxidizes into CO, so it takes care of the coke formation. But also in this reaction, this was found to enhance the selectivity. So this same concept we extended to other reactions like diethyl benzene to divinyl benzene, dehydrogen to various alkyl aromatics, ethane to ethane, and also butane to 1,3-butadiene. So the same concept of soft oxidant, select oxidation reactions to various reactions. Because this ethyl benzene styrene is the monomer for making all these polymers. The concept of catalyst is like this basically. We came out with a mixed rock support, titanium zirconium mixed rocks. On this we have done a lot of work actually. We came out with a review. Vanadium is a well-known oxidation catalyst. Cerium is a very good what you call coke prevention ingredient. That we came out with this catalyst, vanadium, cerium with the combination. So this catalyst was found to be very good for ethyl benzene styrene, but we have gone up to pilot level. As I mentioned, because this combination, zirconia itself only shows 25 square meters, titanium only 15 square meters. But if you make a 50%, so 1:1 ratio, titanium zirconia, also you can go up to 130 square meter surface area. But also this surface acidity also increased with ammonia TPD. We found that this, because this is also very important for activation of the hydrocarbons on its surface. And how because I don't want to go into the details of mechanistic pathway, because without CO2 and with CO2, what is the mechanism in ethyl benzene to styrene, and how cerium oxide promotes the reaction. So this is the final schematic diagram, which is supported by SOBIC, Saudi Arabia, and we hope that this technology goes into production. But because it's a highly mature technology, people have to convince this with this new technology. As I mentioned, we also exploited this reaction to other reactions like ethyl benzene to divinyl benzene, propane to propylene, butane to 1,3-butadiene. So this about the CO2, still work is going on. The last example, I'll go with the energy conversion. So this we all aware that energy conversion is solar, how to harvest solar energy, that quantum process and thermal, both ways we can harvest the solar energy. But unfortunately, the thermal process has not been properly exploited. But quantum, we all know that there is a PVC cells. There are again two types, like single crystal silicon, traditional widespread, but also dye-sensitized. A lot of work is carried out. Still takes time to for commercialization. But thermal, unfortunately, has not yet been fully exploited. So this work actually, this group we collaborated. This work attracted a lot of attention. Very simple actually, simple way of utilizing the thermal energy of solar thermal energy. This is the schematic diagram of the reactor. This is a real reactor. So they actually carried out the experiments. I also participated in this carrying out the reaction at the PSI, the Paul Scherrer Institute of Religion in Switzerland. The concept is very simple. With the concentrated solar radiation, because it mirrors heat the cerium oxide to 59 degrees centigrade. So when you heat the cerium oxide 59 degrees, it loses oxygen, form becomes cerium 3 plus. When cerium 3 plus can be reoxidized with CO2, because it's a tilting type reactor. So because with this is 1500 we can't reoxidize, because we need to decrease the temperature. And 600 degrees, if you introduce CO2, cerium 3 plus becomes cerium 4 plus. In that process you produce CO. Or if you introduce steam, so you produce pure hydrogen. Very simple way of making pure CO and pure hydrogen, just simply with a tilting type reactor. Heat the cerium oxide to 1500 degrees centigrade with solar concentrated solar radiation through mirrors, and produce a CO and hydrogen. So this is the reaction at high temperature loses oxygen. At low temperatures, when reacts with CO2 produce CO, or reacts with steam produce hydrogen. So this is the typical, actually the going temperature when rising oxygen release, and when temperature is 1500 degrees you introduce the pulse of CO2. So this is 1.4 liters of CO, or 1.3 liters of each pulse basically. At 320 grams of cerium oxide, this works up to 1500 degrees, 15 cycles, and each pulse like 1.4 liters of CO or 1.3 liters of pure hydrogen, like basically. So when you make CO and hydrogen, you all know syngas. Why not we make the fuels basically? Solar jet fuel from sunlight, water, and carbon dioxide. So this has attracted a lot of attention. So it's a very simple way of making solar jet fuel using simple water and carbon dioxide and sunlight. Hopefully, maybe in the next 10 years, this may be, see the commercial utility. So because of this to start with, we use the cerium oxide at the temperature required is 1500 degrees. Our goal was to decrease the temperature, because 1500 is quite high temperature, and we need high what you call it, expensive reactor materials to withstand 1500 degrees centigrade. Therefore, we thought we better use the better catalyst. So then we thought using doped ceria. So among various dopants, zinc oxide was found to the best dopant to incorporate the ceria, and for this reaction. So we thoroughly investigated actually why high temperature XRD and TEM, SEM and other techniques. And we got a very interesting results. Like normally when you make the oxide material, we precipitate from nitrates or some other carbonates like thing basically, and calcium 500 degrees temperature to make hydroxide into oxide. So in this case, but unfortunately, this zinc case, we need high temperature. Only at high temperature, 800 to 1200 only, we can incorporate zinc oxide into ceria structure. So that was the observation from our characteristic studies. So these can summarize, like ceria-based nano-oxides are playing an important role in different fields of chemistry, physics, biology, and material science. So one could choose different methods of preparation depending on the quantity of material required. New combination like ceria afnia, ceria tabia, exhibit more activity than the conventional ceria zirconia. Co-doped actually array rates like cerium afnia exhibit much better properties. Among various categories, manganese cerium and iron cerium were found to be the best for mercury elemental mercury oxidation, even at 120 degrees, 150 degrees centigrade. Zinc doped ceria is a promising catalyst for solar energy harvesting via thermochemical conversion. Ceria promoted vanadium oxide supported titanium zirconia is a promising catalyst for oxidative dehydrogenation of ethyl benzene to styrene using CO2 as soft oxide. So this study, as I mentioned, the success rate. So this resulted, although the first paper started in 2003, but I have not updated. It is another 20 papers in this list. We resulted in very good publications, but also got 4 patents, but also book chapters. So I must thank all my students. There are different parts of the world, but also I am very fortunate to find very good collaborators from different countries like Germany, France, Japan, Australia, France, Korea, and Switzerland. And also I got reasonably good funding from various funding agencies. So the last funding was DAE. So thank you so much for your kind attention. Hello.
Hello. Anybody has questions to ask? We can ask them. Okay, it seems no doubt. On behalf of the organization, I would like to a formal vote of thanks to our speaker, Professor B.M. Reddy, who explains nicely the importance of Syria and its complexes, and how to enhance the redox and chemical reactivity properties by doping rare transition metal iron into the Syria lattice and its influences on particle size, and how all this will help to control the environmental pollution and energy conversion. Today, we had an opportunity to hear your thoughts, and this will surely be going to encourage us in our future research events. Thank you so much for your great lecture.
Okay, thank you.
Thank you, sir. So a very good morning to the respected dignitaries, respected professors, and my friends. I'm Ms. Ansari Sadia here, and I'm here to introduce to you all the next speaker for today, Dr. Sadhna Rayalu, ma'am, who would be speaking to us on the topic engineered materials for addressing water and energy nexus issues. With your kind permission, ma'am, let me give a glimpse of the accolades you have received so far. Dr. Sadhna Rayalu is a renowned scientist and head of Environmental Materials Division of National Environmental Engineering Research Institute, CSIR, Nagpur. She is spearheading the research related to materials and catalysis. She is leading a team of green crackers and has made significant contributions in developing new formulations with reduced emissions. Respected ma'am has to her credit around 160 sci publications and around 35 patents for technologies in various fields like functional materials developed for broadband adsorption cell in photocatalyzed water electrolysis system for generation of green hydrogen, plasmonic material-based composites for addressing energy and environmental nexus issues, etc. She is also coordinating various international programs and collaborations, including the Indo-Korean, Indo-UK, Indo-US collaborations. Ma'am has worked with various multinational companies like Alcoa, Horizon Fuel Cell, NTPC, IRA, Agrotech, etc. Having around 100 other publications too. She has supervised the PhD thesis of more than 30 students, and she has to her credit a Best Paper Presentation Awards and local and international awards for material development, including CSIR Technology Award for Green Crackers, Wasvik, and ChemCon, to name a few. Without further ado, ma'am, I welcome you to take the stage.
Hello, good morning to you all.
Morning, ma'am.
Yeah. I'm just sharing the screen. Yeah, can you please see the slides?
Yes, ma'am, it's visible.
Okay. So, good morning to you all. Well, at the outset, I would like to thank the sponsors for giving me an opportunity to share the work which is being carried out at our institute, in specific by the team of research fellows and scientists working in the different areas which I shall be presenting today. So to begin with, I shall give an overview of the advancements that have been made in water and wastewater treatment technologies globally, as well as in our country. And thereafter, I shall try to highlight the role of chemistry, which is the theme of this conference today, that how chemistry can be put into use with specific reference to usage of molecules, materials, and engineered materials for addressing various issues which are revolving around water and energy nexus. So this is the outline of my talk today. I'll start with energy and environment nexus and then illustrate the role of chemistry in resolving issues related to it with specific reference to water and energy. Then I'll be giving you some examples of how these engineered materials have been put into use for disinfection of water, defluoridation of water, and then of course coming to the last but not the least important, that is the climate change impact and how we can overcome those by using the materials for generating hydrogen from wastewaters which emit a lot of greenhouse gases. So just for a very quick introduction about my institute, our institute was initially known as CEPHERI, which is Central Public Health Engineering Research Institute, and it was later on rechristened as NEERI, which is National Environmental Engineering Research Institute, way back in 1974. Our mandate definitely is water and sanitation, which is the theme which I was given to give a talk on issues related to clean water and sanitation. So it is the mandate of our institute. And besides that, we deal with all aspects of environmental science and engineering, including climate change. So this slide basically illustrates the role of chemistry with specific reference to use of molecules and materials in addressing various environmental issues. So there are three different components essentially when it comes to environment, that is air, water, and solid. So when it comes to air, our team has developed the new pyrotechnic formulations which have been put into use in the green crackers, which are now there in the market. And I'm sure you must be knowing that there is legislation and ruling from Apex Court that now onwards only the green crackers can be put into use in our country. So this is the way chemistry has been put into use, put into application for an issue which resonates very well with the general public. Besides that, we have enhanced the efficiency of the functional PV panel, which I shall be touching upon. We are working on using these materials for generation of hydrogen and controlling the GHG emissions from water and wastewater. We work a lot on removal of color and fluoride, which I shall touch upon. Of course, solar disinfection. We convert waste into high value added products, like we have developed cyanospheres from fly ash. Then we are converting waste into char. Menstrual waste has been converted into char and we call them as SSR. And last but not the least is SSR, in which we have worked a lot, used the different materials and the engineered materials for COVID management, and we are working extensively in the area of menstrual waste management. So in this talk today, I shall be focusing majorly on clean water and sanitation, which was the theme I was supposed to be speaking on. And when it comes to clean water and sanitation, SDG 6, that is the Sustainable Development Goal 6, in which there are 6 outcome-oriented targets, and the ones which are highlighted, that is the safe and affordable drinking water and wastewater treatment with specific reference to its reuse, shall be touched upon in my talk today. These are some statistics on water. These are all available in the literature there, but I'll just quickly highlight a few. It is estimated that by 2040, 1 in 4 of the world's children under 8 2018, and it is around 600 million in all, will be living in areas of extremely high water stress. Over 2 billion people living in different countries are experiencing high water stress. But the most important fact is that the climate change scenario is having a very adverse effect on water scarcities and water related issues. And it is expected that more than 24 million to about 700 million people will be displaced because of the issues which are related to climate change impacts. So these are some of the statistics which are definitely very scaring. As far as our country is concerned, most of us are aware that we have a lot of water scarcity issues. It has been predicted by Niti Aayog that nearly 21 Indian cities will run out of groundwater by 2021, which definitely highlights the need for urgent and improvements in water management. So coming back to the energy and environment nexus issues, well, it is something which is a strategic issue, and it's being addressed across the globe for improving the quality of life and maintaining it as well. So let's take for an example thermal power industry to understand what energy and environment nexus is all about. What it says is that when in the thermal power industry, we process coal to generate energy, and while we are processing, there are a lot of operations done which requires water, like in the cooling tower, the coal washeries, the pond effluent, so on and so forth. So while making electricity, we are using a lot of water. Now, when this water is generated or the wastewater is generated, we are treating. So the treatment of the water requires a lot of energy. And this is what is all about the nexus we are talking about. And it has extensive work is being going on in this direction. At our institute, what we are trying to do is to identify the hotspots and deploy various interventions. They could be catalytic or otherwise, to make the systems energy neutral. That is the energy which is required in treatment of water. If we can substitute with solar energy, then definitely it will bring down the energy requirement. Similarly, we are trying to see how best we can use the energy which is embedded in the waste to generate energy. Like we are trying to generate hydrogen from wastewater, which I shall be talking about. So this basically summarizes the water and energy nexus. As I've already mentioned, the extraction, refining, fuel production, etc. definitely requires water. Similarly, for treatment of any kind of system, you require energy. So this is what water and energy is all about. And then if we are trying to make these systems energy neutral by employing different water and wastewater treatment systems, if we have to make them energy neutral or positive, the solution lies in using renewable energy. And when we talk about renewable energy, solar energy has a very important role to play in our country by virtue of the fact that we are lucky to have at least 300 days of solar energy. But before I go into the solar energy and its application to make the systems energy neutral and energy positive, I'll quickly take you through the different efforts which have been made at our institute. These are some of the traditional water and wastewater treatment systems which have been put into use since the 1950s, So we have a lot of systems, like we have the oxidation pond, wherein the coke oven effluents, the steel effluents are generated, the aerated lagoons. Then, of course, the tannery waste or the Kanpur was still. And then we developed the disinfection tablets. This was developed way back in 76 for disinfecting water, which was essentially based on chlorine tablets. Now, of late, this is a technology which has picked up a lot in our country, wherein the plants are being used for treatment of wastewater, essentially to remove the nutrients and the organics which are there. We have built several CETPs. So all this work has been done by our institute across our country. What I wanted to highlight is this is the latest technology of our institute, which has been demonstrated across the country. It's an advancement. as compared to phytoric technologies, which can also be put into treatment of nala, so on and so forth. So these are the traditional technologies which are being put into use, and this basically summarizes what are the issues which are related to the traditional water and wastewater treatment units or systems which are existing, which are taking care of it. First and foremost, the biological wastewaters, as I've already mentioned, are very energy intensive. So how can we make it less intensive is the issue. We can try to use solar energy over here. There's a lot of embedded energy in the water and the wastewaters, like the organic carbon and the nutrients, which are presently not being put into use. So the advancement in the water and wastewater treatment systems could be to use this embedded energy. So there's a paradigm shift which is required in the way there are traditional water and wastewater treatment existing as compared to the advancements which can be introduced. And this is what we are trying to address at our institute. So this basically summarizes the various limitations which are there in the water treatment systems. First and foremost, we lack portability for emergency response or use in remote locations. The solar energy has not yet been put into use extensively as far as water and wastewater treatment. We are still our treatment systems are still based on usage of large quantities of chemicals and electricity, and our systems are not adapted to changes in source water like emerging contaminants and the climate change impacts which will inevitably be there. So what we are basically targeting now is to use advancements in nanomaterials that could be helpful in transforming the existing systems to operate modular treatment systems, which would essentially reduce the footprints. Now, why the emphasis on solar energy as far as water and wastewater treatment is concerned? So these numbers clearly show that the global need for the energy is about 15.7 terawatts for us, as compared to that what we have from solar energy is about 1.75 into 10 raised to 5, which is 10,000 times more than what we require. So even if we cover the earth by 0.1% of the with the PV, and having 10% conversion efficiency, the solar energy is able to take care of all the needs which are there for energy. So forget about using for all the other energy consumption. We can use this at least for systems in which it can be deployed, like for water, making the water and wastewater systems energy neutral, so on and so forth. And why we should be doing it in our country? Because solar energy is available for nearly 300 to 330 days in our country. We have about 5,000 trillion kilowatt per year of solar energy with us. And that's why a lot of emphasis is now being given to usage of solar energy in different water and wastewater treatment systems. And I shall be giving you the examples wherein it has been very effectively put into use for targeting different pollutants. Now, that was all about solar energy. Now, coming to the role of chemistry with specific reference to engineered materials. Now, environment is a multidisciplinary area, and we realize that to address different issues, we cannot keep on developing materials and molecules. What we could be doing is we can tailor the property of the materials in such a way so that we can address or take care of wide array of pollutant. So with this in background, we started with this concept of engineered materials, in which case we are trying to develop materials, that is the synthetic analogs of some natural materials which are available, or modify the materials and tailor its property by in situ modification or ex situ modification. Now, when it comes to ex situ modification, we are like incorporating certain metals in titanium, which is a very widely used photocatalyst, like we incorporated gold, platinum, so on and so forth, which enhanced its efficiency for absorbing the visible light. Ex situ, what we are, this is ex situ. In situ is while we are doing the synthesis, we are incorporating certain metals, which makes it very selective for targeted applications, like we have developed materials which are very selective for fluoride, so on and so forth. And the natural analog, of course, is the zeolite mineral, which is existing. We are making synthetic analogs and then tailoring its property for different applications. So these are the wide array of materials which have been synthesized by us. I'll not go into the details of this, but this is one of the most advanced materials which has come. These are materials which are targeting for single application, but then we could design the materials in such a way so that it can have multiple applications. Like we can have a core shell structure of silica, silica as the shell and the core as magnetic core we can have, so that when we are using it in the water, we can easily remove it by magnetic separation. And at the same time, the silica can have different functionalities, like we can introduce certain metals which are very selectively having bactericidal properties. Then we can select ions which have catalytic properties, so that they are multifunctional. This is how the advancements is going as far as the material design is concerned, and this is what we are doing at our institute. There are different kind of materials which have been designed by us, patented and published. It's all there in the public domain. You can browse through it, and if you have any kind of particular questions, we'll definitely get back to it. So one of the materials on which we have worked extensively is the fluoride materials, and these are some of our publications related to this. This was carried out as part of a project which was sponsored to us by UNICEF, and a very simple technique was developed in which you can sprinkle the water in the pond, just shake it, and then you have the treated water which is having fluoride less than 5 ppb, which is the requirement, less than 1 ppm, which is the requirement. So the different kind of materials which have been developed by us, the materials which were available in literature are usually having absorption capacity in the range of about 10 to 12. But yes, we have designed materials which will give us huge capacities ranging from 30 to 40 milligram per gram, and they are highly selective. They have been put into use for removal of water. It was not restricted to lab, but it has been very well demonstrated at nearby villages of Nagpur, as well as this technology has been demonstrated very well in villages of Bihar which are suffering from fluorosis. Now, these materials have been put into use not only for water treatment, but they have also been put into use for a treatment of wastewaters being generated from aluminum industry. So this was a project which was sponsored to us by multinational, that is Alcoa, wherein we were successful in developing the material and treating the industrial wastewaters which were there. And this has resulted in a joint multinational patent. So these are some other advancements which have been made in our group in different multifunctional materials. To start with, we have developed plasmonic materials showing photothermal property, plasmonic materials showing photocatalytic properties, and then we have put them into use for solar water disinfection. As seen over here, it is not restricted to material development, but we have designed different modular systems which have been taken into the slums in different parts of our country, like Noida, Savda, Bundelkhand, in Mumbai, Worli in Mumbai, so on and so forth. So these are the different kind of materials which were designed, and then they were put into use for solar water disinfection. Now, globally also a lot of efforts are being made. So this was a very interesting paper which I came across from Hala's group. She happens to be one of the pioneer as far as photothermal properties concerned. Membrane distillation is being put into use very extensively. So what they have done is that they have incorporated a layer of photothermal material which on radiation gives you evaporation of water as against the heat which is required for the saline water to be given for it to undergo thermal membrane distillation. So this was a very, very interesting application, which is of late finding very huge application as far as wastewater treatment is concerned. So I'll quickly take you through the application of chemistry in designing different kind of materials, which resonates very well with public as far as the RO reject treatment, grey water treatment, and water treatment is concerned. So these are the three different category of materials. The first material deals with plasmonic materials for photothermal heat, wherein we have been majorly focusing on carbon support material. And what is the plasmonic property? I'll just discuss with you in the next few slides. So because it's a very, very important property based on which you can have a water treatment facilities targeting wide array of pollutants. So second category is photothermal material, also having catalytic property. Like in the case of TiO2, we can have certain metal nanoparticles like silver, gold, and so on and so forth, so that this plasmonic property can be there in that. And what is plasmonic property is illustrated over here. When a material is subjected to solar radiation, then the metal nanoparticle or the carbon nanoparticle essentially undergoes oscillations, which creates the electrons and the holes cloud. And these electron and hole clouds, when they are not put into use and they combine, they generate a lot of heat. Now, this heat is what photothermal heat is all about. And then this photothermal heat can be put into various applications as far as water and wastewater treatment systems are concerned. They can be used for disinfection. We all understand that if we subject water to high temperatures, the microorganisms will not be there. They will be deactivated. Then a lot of evaporation and distillation applications can emerge. So this is what we are doing in designing the different plasmonic materials. And this figure highlights the importance of the plasmonics. As I've already mentioned, when we subject the metal nanoparticle or the carbon nanoparticle to solar radiation, then there is a collective oscillation of the conduction band electrons in the nanoparticle, which is essentially driven by the electromagnetic radiation. And when this combines, you get the thermal heat, which is being exploited. It has been reported that the temperatures can go up to 1000 K if it is manipulated properly. So as I've already mentioned, this is the lady who has carried out the pioneering work as far as application of plasmonic composites is concerned. They use the different plasmonic materials for sterilization of human waste, which is a very big application. Based on the work which we were following, then we applied these designed different kind of materials and tested it for disinfection, sterilization, and several other applications. So photocatalyst, I'm sure most of us understand that when we subject any material to solar energy radiation, the electrons and the holes are created. Electrons can do the reduction reaction and the holes can do the oxidation reaction, which is a downhill reaction. Now, these applications are being extensively used for water and wastewater applications, like they can be used for sterilization, pollutant treatment, so on and so forth. So we have designed different photocatalytic materials as listed over here. We basically have designed the carbonized titania composite, in which we have the carbon nanoparticles deposited on titania. Then these are the silver nanoparticles which have been deposited and they have been put into use for various applications. We have also designed the nano composites using biopolymers like chitin, chitosan, alginate, so on and so forth. Last but not the least, silk cocoons are proving to be very, very effective in designing different kinds of gels, fibers, etc., which can be embedded with metal nanoparticle and then they can be put into use. The first application for which we tested was solar disinfection. Well, I'm sure you all understand that due to climate change impact, there are a lot of things happening. It has a huge impact on sanitation, because of which there'll be a lot of discharge of the sanitary waste into the water and wastewater treatment, obviously leading to a lot of diarrheal diseases. Our country is already having a huge problem of diarrheal diseases. It has been reported that diarrheal diseases are basically responsible for 19% of the total number of deaths which are happening. And in our country, approximately 2 million deaths are reported every year due to diarrhea. There are a lot of methods available like boiling, chlorination, so on and so forth. They have their own pros and cons, which I'm sure most of you understand. But a very simple technique of solar disinfection, that is SODIS, was introduced by Institute of IVAG, that is a Swiss Federal Institute of Aquatic Science and Technology. Of course, it is very effective. You can put water in a bottle, keep it on the rooftop, and it will get disinfected. But then there are a lot of issues. It does not reduce the count, the total microbial count. First thing, it is subject to climatic conditions. Then if the water is turbid, if there is turbidity in the water, then of course it is not very effective. So to overcome the issues which were there in SODIS, we employed different methods, and I'll be sharing some of the results pertaining to this, wherein we have used a combination of UV and photocatalysis, UV and thermal and photothermal method. These are the three different methods which have been employed by us for a disinfection. We all understand that UV is being used extensively, but it is energy based. The lower it has, the shelf life of water is lower because UV, it just impairs the DNA, which has a chances of getting repaired. So microbial contamination may reappear. However, if we use a combination of UV and photocatalytic, then the microorganisms go into CO2 so that we don't need any kind of polishing, and then the shelf life of water is higher. Same applies with the UV and thermal. So keeping all this chemistry and materials into background, we have designed the different systems which are shown over here using the different materials. This is for personal use. It's a kind of pouch in which you can fill up water, expose it to sunlight, and then you have water to the tune of about 2 to 3 liters in just 15 minutes. Then this is for a family use, wherein you can get about 15 liters of water. In this case, you can get about 200 liters of water. So all these systems have been very well tested, and they have been demonstrated in field. But what I would like to show is this pilot plant, which has been designed by us, wherein we can get nearly 30 liters of water within 15 minutes, and it's catering to the needs of about 750 personnel at our institute. Disinfection time is just about 15 minutes, and then the catalytic efficiency is huge. There is a nil count starting with 6 log reduction. So this is operational based on the different materials which have been studied by us. The novelty in this method was the in situ chlorine and hydrogen peroxide generation by using titanium and copper chloride combination, which resulted in almost 100% disinfection of water within 15 minutes. Besides that, these are the different systems which have been designed by us. We call them as instants for these because in this case, the zeolites have been embedded with the metal nanoparticles, and when they are exposed to sunlight, lot of exothermic heat is generated, because of which 6 log reduction has been observed within 10 minutes. So these are the different kind of systems which have been designed by us as far as disinfection is concerned. Now, taking this photothermal material forward, we are now working on a solar water distillation, which we call it as SWAST. What happens in this case is there is a system in which you keep the contaminated water along with the photothermal material, and it is exposed to sunlight. When it is exposed to sunlight, the thermal heat from the sunlight as well as the photothermal heat facilitates the evaporation, and then it condenses, and then what you get into an outlet, and then what you get is a distillate which is pure as compared to the contaminated water which has been taken. So these lot of work has been done as far as distillation is concerned, and the advantages are that the system is relatively cheap, it has low maintenance cost, it can be used at household level, it can be scaled up through different pragmatic, programmatic approaches. Then there are no energy costs, and of course it's entirely based on solar energy. So we have tested these systems for RO rejects as well as the gray water. Gray water, I'm sure you all understand, is the wastewater which is being generated in the household or office streams, which is generally not contaminated, not having fecal contamination. We've been focusing on treating kitchen wastewater and RO rejects. I'm sure you all understand. We use RO treatment in our home to get purified water. But what we have to understand is that any RO purifier, if we have, it is generating about 3 liters of water for every 1 liter of purified water. That means only 25% what we get is the water, purified water, and 75% comes out as RO rejects. We are trying to treat these RO rejects and gray water using the solar distillation, using different carbon materials. And why carbon materials? Because they are low cost, efficient, robust, and they have all these properties which are essentially required for them to be put into use for generating localized heating for distillation method. That is, they have broadband sunlight, they absorb right from UV to IR. They are very good as far as thermal management. They facilitate water evaporation. So because of these properties, it's being put extensively into use for solar distillation. And this is a very important publication from our group in which we have designed carbon nanoparticle from a very, very simple method, which is based on generating carbon nanoparticles at home, like we make kajal by burning candle, or by using a different kind of oils. These carbon nanoparticles can be generated, and they are showing very good photothermal heating. They have been put into use in these different systems, which we have called as SWAS, that is solar water distillation. And we tested it in different configurations, and one of the best configuration which has emerged is this system which you are seeing. It's a kind of pyramid solar distillation which has given very good results as compared to the conventional distillation units which are there in the market. The most important is the use of photothermal materials in the design, which is a new design as far as solar distillation, has resulted in enhancement in productivity. That is, the distillate which is coming out from the contaminated water has increased by a factor of 2. That is, the conventional unit, when subjected only to solar light, gives you 2 to 3 liters per day. Compared to that, we get an output of about 5 to 5.6 liter per day, which was a significant improvement. And the best part of it, that before and after treatment, the quality of water which is emerging for the RO reject is meeting the Indian standards which are stipulated for the different parameters. In all the cases, the parameters are meeting the Indian standard. So that was a very good a development for us. Now coming to the last section, then how water and sanitation is linked to the climate change and what we can do in this context as far as chemistry, materials and molecules are concerned. So I'm sure you all understand about climate change. Climate change is majorly influenced by the greenhouse gases. And when we talk about greenhouse gases, most of us talk of only CO2, but it's not the case. There are a list of GHGs, including nitrous oxide, methane, etc., which is influencing the greenhouse gas effect, which leads to global warming, and in turn the climate change impacts are there, which is causing a great concern to the water supply systems, because it is damaging the infrastructure because of flooding which is happening. Then there's loss of water sources due to declining rainfall rainfall, there's a lot of disturbances in the distribution of water. So all these factors are getting affected. The ones which are highlighted are the ones which needs to be addressed as far as water is concerned. And then climate change is influencing the sanitation, which in turn is affecting the carrying capacity of waters which are receiving the wastewaters from these sanitary facilities. So the most important, of course, is the wastewater treatments are emitting a lot of CO2, methane, and N2O. So we have to integrate a lot of advancements in the water technologies, that is advancements in the traditional wastewater technologies, so that we are able to address the climate change issues. So these are some pics of climate change impacts, and we all understand that the fury of nature, there's a lot of floods witnessed in Mumbai, Chennai, Kanyakumari, so on and so forth. And this pic basically essentials how sensitive these zones have become. Besides floods, there are droughts, earthquakes, coldest days, landslides, so on and so forth happening. And it is all because of the different greenhouse gases I've already mentioned. CO2 is not the only greenhouse gas. Methane and nitrous oxide is also of concern, and the global warming potential of these gases is significantly higher as compared to CO2. Methane is generally emitted when we are going in for anaerobic wastewater treatment, and if it is having a lot of nitrogen, the wastewater, then obviously a lot of nitrous oxide is also generated. So these are the different emission scenarios, that is the GHG emission coming from different sectors. What I wanted to highlight is the emission which is coming from waste. It is about 2.65%. And the concerning aspect is from wastewater itself, there is about 2% contribution to the GHG emissions. And this is majorly the CO2, methane, and N2O coming from the different wastewater treatment processes, which I have already mentioned. So to address this issue, we are carrying out extensive work at our institute. We are trying to treat the seawater, the RO rejects, sewage, so on and so forth, using different approaches. And this is one particular system which we call it as SWAR, that is the solar water electrolyzer, which has been developed by us. SWAR meaning voice, which we all understand, is having two components. One is the functional panel, in which we have introduced a lot of modifications by way of different molecules and materials. And this functional panel has an efficiency which is higher than the commercial panels. Like if the commercial panel is about 15%, this is about 23 to 24%. And this is all because of the chemistry, the molecules and materials which have been applied. Similarly, water electrolysis is a very mature technology. It is reported, but then it is very energy intensive. And the issue of this has also been addressed using different molecules and materials, which I shall quickly take you through. So this SWAR is a decentralized option which is being explored for sewage treatment, for water conservation, which definitely has reduced carbon and environmental footprint. For this, we have designed different materials. These are some up conversion and down conversion materials which have been designed by us. Down conversion is we take UV and convert it into visible light so that it is absorbed by the panel. And up conversion is that we take, let's say, IR and then convert it into visible so that we get it. So by using different kind of materials, we have designed the functional panel, which as I've already mentioned, has enhancement in efficiency up to 22.2%, right from 18%, by using a different kind of materials in different ways. If we coat the panel, we prevent the deposition of soil, particulates and microbial, which increases the life of the panel. And at the same time, it reflects UV, which is bad for the panel, because if we expose the panel to UV, a lot of heat is generated. Similarly, IR and heat is very bad for the panel because it encourages the recombination reaction, because of which the efficiency decreases. So here again, we have applied molecules and materials which absorbs the visible and the IR light and leads to enhancement in efficiency. So the panel, which is initially having 18%, can go up to 22 to 24% by using different kind of molecules and materials for absorbing UV, visible, and IR. And that is why we call it as broadband absorption cell, because silicon takes only visible, but when we apply different materials which takes up UV and IR, then it becomes a broadband absorption cell, which is what we call the functional panel designed by our institute. Then, when it comes to water electrolysis, here again, we have reduced the requirement of water electrolysis by using different systems, different molecules, like we have identified different donors which can be put into use, which would essentially reduce the capex, that is the capital cost, and the operating cost, that is the electricity requirement. And then we have designed electrodes which are PT free. Because of this, there's a significant reduction in the hydrogen that's being generated. The hydrogen that's being generated presently using water electrolysis has a cost of about 350 to 400. However, we have been successful in reducing the cost to about 100 to 120. These are results of a system which is running continuously at our institute. These are the different designs which we have made for water electrolysis using a different kind of wastewaters which have been put into use. And these are some very interesting results about the HPB redox shuttle, which has resulted in exemplary results as far as hydrogen, and the electricity consumption has reduced to the tune of about 50%. And to generate these redox shuttles, we use a lot of photocatalysts. These redox shuttles are basically HPA, that is heteropoly acids, like silicotungstic acid, phosphotungstic acid, so on and so forth. And these acids are prepared using different photocatalytic materials. So we have a grip on designing different kind of photocatalytic materials, and we've been working in this area for more than a decade. And we are using these different photocatalytic materials to prepare the redox shuttle, wherein HPA, which is the oxidized form, is reduced to HPB using the photocatalyst, and then this HPB can be used in the water electrolyzer to reduce the electricity consumption. These are the different photocatalysts which have been very effectively put into use for generating the catalyst and in turn reducing the electricity requirement of the water electrolysis. Coming to the last slide now, this is how we are preventing the release of CO2 from wastewater. We all understand that when wastewater, which is having organics, is treated aerobically, then we generate CO2, which obviously is a greenhouse gas. Now, this can happen. This can be avoided by using water electrolyzer, in which we can be having a microbial electrolytic carbon, which is the anode, which would definitely generate the CO2, or we can have anodes based on titanium, stainless steel, so on and so forth. It would definitely generate the CO2, but then this CO2 can be taken into another water electrolyzer, wherein we can have the anode in the form of calcium, which would react with the CO2 which is coming from the previous reactor, react with it and generate the calcium carbonate, and then the electrons which are flowing to the cathode can generate hydrogen. And you can see that we got exemplary results from sewage which were treated in a electrolyzer. The CO2 which was coming from there was then taken in another application. So this is the last slide. We have a solar energy park at our institute, which is now being converted into an innovation center, wherein different kind of systems have been put into place, whether it is SWAS, that is solar water distillation, SWAR, that is solar water electrolyzer, for treatment of sewage, RO rejects, so on and so forth, wherein we are generating hydrogen. So we have a lot of participation from different countries like UK, US, Australia, Japan, so on and so forth, and we are working in these different areas which have been listed. So this is the team which was working with me in this area of water advancements in water and wastewater treatment technologies and how they can be put into use to make the systems energy neutral, if not energy positive. So with this, I would like to conclude the presentation, and if there are questions, I would definitely address them. So thank you so much for a very patient listening.
Thank you so much, ma'am. Any questions to be asked, please, the platform is open. You can post your questions and doubts in the chat box. So there's a question here, ma'am.
Yeah, please. I saw that can we use tin or indium for enhancing the efficiency of panel? See, when we are putting into use any kind of material, first and foremost, you have to see that it does not affect the transparency in any way. Okay, so like if you talk about indium or about tin, normally the kind of electrode which is designed with it, as far as my knowledge goes, would not be transparent. So that is one particular thing which you have to bear in mind when you are designing or planning to use any kind of material to enhance the efficiency of the panel.
Thank you, ma'am, for the answer.
Yeah.
So any further questions? Okay, so I would like to propose a formal vote of thanks to ma'am. So thank you, ma'am, for such a lucrative and informative session. Indeed, your extensive contribution related to the wastewater management has been really, appreciative. And 600 million is a huge number indeed to be under high water stress, and you made us aware of this issue. So thank you for bringing us to that. And your contribution in the invent of the new technology using solar energy in wastewater treatment will definitely be a boon to the wastewater management. The sun is definitely shining very bright nowadays, so it's the right time to study your application. And nanophotonics enabled solar membrane distillation. It was an interesting application to be studied for wastewater treatment. Even the plasmonic materials as well as the mechanism of Swadis. There's a quote by Benjamin Franklin, which says, when the well is dry, we know the worth of water. So you have indeed made us aware and alert towards its worth and treatment. And thank you so much for giving us your valuable time. So now here we shall take an hour break for lunch, and you all are expected to rejoin at 1:30 p.m. sharp. So thank you so much.
Thank you.
Good afternoon, everyone. Myself, John T. I hope you all have had your lunch because we are starting with the afternoon session of the national conference. Okay, it gives me great pleasure that I have the opportunity to introduce Professor Banage, who is a scientist of great repute. Professor Banage obtained his doctoral degree from National Chemical Laboratory in 1995 and spent several years in Tohoku in various positions. He joined Institute of Chemical Technology as a professor of industrial and engineering chemistry in 2003. He was the Dean of Infrastructure and Campus Development during 2014 to 2021. He was the head of Department of Chemistry during 2009 to 2014 and then from 2021 onwards. Professor Banage has contributed in areas of catalysis for activation of small molecules like carbon dioxide, carbon monoxide, and hydrogen from various reactions. He has developed novel strategy for various reactions like Heck, Suzuki, Sonogashi coupling reactions, their carbonylated form, hydroformylation, amino carbonylation, alkoxy carbonylation, amination, hydrogenations, etc. The work is focused on developing strategies for catalyst products separation and catalyst recycle. He has developed several homogeneous transition metal-based catalysts for these reactions and solid-based catalysts for carbon dioxide fixation reactions. He is also an active researcher in the field of nanoparticle synthesis and its catalytic activation applications, enzymatic catalysts, etc. He has published 441 research papers in international journals, 29 book chapters, and he has 34 patents in his name. He has received more than 15,150 citations with an H index of 64 and I-10 index of 329. For those who don't know, I-10 H10 index is a number of papers that have more than 64 number of papers that have more than 64 citations, and I-10 is the number of papers that have more than 10 citations. He has guided 48 doctoral students and is currently guiding 15 research scholars for their doctoral research. He is the fellow of the Indian Chemical Society, Royal Society of Chemistry, Biotech Research Society of India, and Maharashtra Academy of Science. I'm sure that you will find Professor Banage talk to be both informative and inspiring, and I'm sure that you will enjoy meeting him. Without further delay, let me hand over the session to Professor Banage.
Okay. Good afternoon to all of you. And first of all, I would like to thank organizers of this conference for inviting me to deliver a talk. And today I will talk on how one can use the catalysis for biomass derived product. I request the organizers to allow me to share the screen.
Sir, yes, sir.
I request to allow me to share the screen. Okay.
Sir, you are the co-host. Now you
Okay.
can share the.
I hope all of you can see the slides.
Yes, sir, we can see.
Okay, fine. So, title of today's talk is Biomass Derived Platform Molecules to Various Value-Added Products. So, today we'll discuss about how catalysis can help in this type of transformations. At ICT, we are working on various aspects of the catalysis, primarily preparing homogeneous catalysis, reaction kinetics. We also do preparation and characterization of organometallic complexes, focuses on catalyst product separation techniques in homogeneous catalysis, such as biphasic catalysis, supported liquid phase catalysis. We do carbon-carbon coupling, carbon-nitrogen coupling reactions, preparation of ionic liquid, CO2 and CO-based reactions, and of course, biocatalysis using enzymes. And most of our work is focused on developing sustainable chemistry, which is a theme of this conference. So based on the theme of the conference, today's topic is chosen to show that how catalysis can do the useful transformations. For example, after biomass fractionation, you get lots of platform molecules. And one can develop catalyst in which you can tune the porosity, size, and morphology of the catalyst. You can also enable your catalyst with either acidic or basic sites or redox site. So such type of catalyst can do the transformation of such biomass derived molecules. So I would like to share the work related to that. So first, I would like to show that how HMF, which is derived from biomass, this is one of the platform molecule, can be converted to DMF, and DMF is useful as fine chemical. So this work we have published a couple of years back. So we have developed a catalyst for this, and that work I would like to share. If you look for the previous reports, when we started this work, the catalyst system was very expensive, very high temperature, long reaction times, and leaching was a major problem. They also need co-catalyst. So we have developed very inexpensive catalytic system and useful one to develop such type of thing. The product which we have focused is 2,5-dimethyl-furan or DMF. It is an important transportation fuel because of high octane number, greater energy density, and very good boiling point, lower oxygen content, calorific value compared to the poor water solubility. So the catalyst was prepared is ruthenium supported on zirconia MCM41, the typical method which we have followed. Is we have taken zirconium MCM41 and dissolved ruthenium chloride in ethanol, and subsequent reduction with sodium borohydride. We got the ruthenium metallic site, and filtration, washing, and calcination gives us ruthenium deposited on zirconia MCM41 catalyst. We have done ammonia TPD, and we have confirmed this acidic site. Also, morphology was confirmed. The catalyst was well characterized. You can see here from EDF mapping that all the components like ruthenium is red one, zirconia, oxygen are uniformly distributed, showing that the catalyst is what we need is prepared, and EDAX analysis also confirms that. So various compositions were prepared and elemental mapping was done to ensure that all the components are present on the catalyst. The reaction which we had selected, as I told you, DMF synthesis is not so simple because lots of multiple products are possible during this transformation. You can see that HMF, one can do the hydrogenation to prepare 5-methyl-furfuran. Also, you can prepare by hydrogenation 2,5-bis hydroxymethylfuran. Further hydrogenation, it will give you 5-methyl-furfuryl alcohol, and further hydrogenation, it will give you DMF. Further hydrogenation, it will give you 2,5-dimethyl tetrahydrofuran. So our focus is to selectively prepare DMF because multiple products, you can see that it is possible just by the hydrogenation. So for that purpose, we have screened various catalysts, and you can see that they are either based with palladium, ruthenium, gold, nickel, many metals we have explored. And we observe that ruthenium gives the best result for the DMF preparation. Is recyclable. You can recycle it n number of times. We could able to see that it also indicates that ruthenium is not leaching out and you can get a stable catalyst. The reaction mechanism is based on the sites which are present on your catalyst. For example, you can see that suppose you start with this substrate, we have metal here on which hydrides are there. They will transform an acidic site, it will dock to this oxygen. And because of docking of this substrate on the acidic sites present on the catalyst, hydride transfers can take place and subsequently you will get the product. So recycled catalyst also confirms it retains its morphology, it retains its structure as such. Besides that, we have done another experiment. As earlier I showed you that HMF can be converted to DMF, that is 2,5-dimethyl furon. But we can go back further, and from fructose you can get the HMF, and HMF can be converted to DMF. So you can do either both ways, that is step 1, or you can also combine these steps to do the one-pot dehydration followed by hydrogenolysis reaction to give you the DMF. So this catalyst is very useful to prepare DMF. In the next platform molecule, that is levulinic acid. Again, levulinic acid can be derived from biomass. And what we have done here, we have developed a graphene-based catalyst in which ruthenium is docked on this graphene. And this is docked because these ionic liquids were also anchored on the graphene. And because of this ionic liquid, they can act as some kind of docking agent or ligand, which can dock the ruthenium catalyst here. The levulinic acid, we have cyclized to prepare pyrrolidons. So this work last year we have published in JCAT. You can see that we can prepare pyrrolidons using such type of catalyst. I would like to give more details about this work. Again, lots of applications of pyrrolidons. You can see that they are value-added chemical products as solvent, chelating agents, surfactants, intermediate forming, agrochemical components, and so many applications are there for pyrrolidons. The catalyst which we have prepared is ruthenium docked on graphene oxide ionic liquid, that is GOIL. So you can take ionic liquid and react that with 1-methyl-3-trimethoxysilyl propyl chloride, is this one, and ionic liquid will get anchored on this particular silyl group, and this silyl is further anchored on the graphene oxide. So you get the moiety on which you can now put the ruthenium chloride so that you get the ruthenium chloride immobilized graphene oxide catalyst. Again, this was characterized by all the tools. It confirmed its structure. It is stable up to 200 degrees centigrade. XPS also confirms the presence of ruthenium and its oxidation state. Same tells you about the morphology of the catalyst. Now the reaction which we had focused. So levulinic acid, which is a platform molecule, you can couple that with benzylamine as a again model reaction. You can see that cyclization followed by this incorporation of N is there in the cyclic ring. So you can prepare 1-benzene 5-methyl pyrrolidine to all using such type of catalyst. So when we did the screening studies for this catalyst, ruthenium was the only active metal which we have found in solvent methanol, and it can give 93% yield at 130 degrees centigrade and 5 hours. So these are the optimized reaction conditions. And this is a typical concentration time profile. And you can see that reaction works very well with levulinic acid. Now, once we know that model reaction works, we have extended this for different types of amide. We have different types of substitution on this R. You can see the red component which we have changed, and you can prepare different types of pyrrolidone molecules using same method. So typically works at 120 degrees centigrade, 15 bar hydrogen pressure, and 1:1 ratio of amine to levulinic acid. Cyclization can happen very easily. Now again, like the previous case, in which we have coupled two steps together, here also we have attempted. For example, levulinic acid, as I told you, is a platform molecule, can be obtained from fructose. So if you give acid treatment to fructose, you will get the levulinic acid, and levulinic acid with amine will get the pyrrolidones. So you can also use biomass waste with acid treatment to prepare levulinic acid, and again you can do the pyrrolidone synthesis. So we have backward integrated this also with the original feedstocks. Now, using same logic, we have prepared different molecules. For example, synthesis of N-substituted isoindolinones. So you can take such molecule and react with the amine. You can prepare the isoindolinones type of substrate using same methodology. So this is a possible reaction mechanism. You can see that amine, then it forms imine, then imine gets hydrogenated, and then followed by cyclization by dehydration. So catalyst is recyclable. It works very well for several of these cycles. Catalyst was characterized for its retention after recycle. Also, it retains its performance and also structure. So recycled catalyst was again characterized. So this is the way to prepare pyrrolidones from levulinic acid as a platform molecule. Further, we have prepared another molecule, that is 2,5-diformylfuran. This is the structure of 2,5-diformylfuran. This is an important intermediate in pharmaceutical and fine chemical. So how it is possible? You can take biomass, fructose. You can do either one-step synthesis, that also we have achieved, or you can do the two-step synthesis, in which first dehydration of fructose will give you HMF, followed by oxidation, it will give you the DFF. So both ways you can achieve the goal, or in this case, if you want HMF is also, you can prepare. This work was published last year in NJC. The product here, DFF, is a application product in furanic polymers, liquid fuels, antifungal agents, heterocyclic ligands in pharmaceutical, fungicides, and renewable furanuria resins. So the catalyst which we have prepared here is ruthenium supported on montmorillonite K catalyst, so K10 basically. And we have supported this ruthenium on K. And the catalyst which we have got is ruthenium 0 nanoparticle size, which is supported on Mont K10. So this is the XRD, which tells you about the structure confirmation. XPS EDX mapping shows that all the components are present in uniformly distributed. TEM also shows and confirms that we got the ruthenium in nanosize. HRTEM again confirms the structure of ruthenium. You can see that this is 5 nanometers, so ruthenium is about 5 nanometer size. EDX also confirms its structure. Thermal stability data also gives you the idea about the stability of the catalyst. So HMF conversion and TFF, you can see that how HMF is converted and you get the DFF. So pressure, solvent, catalyst loading, all these parameters were optimized. We again attempted here one-pot synthesis from fructose directly. We have prepared diformylfuran using such type of catalyst. So catalyst is again recyclable here, and recycled catalyst retains its structure. You can see the studies with respect to the recycled data. Besides fructose, We have also attempted to prepare DFF from various carbohydrates like glucose, sucrose, inulin, raffinose, various sugars, maltose, starch, various types we have tried. And this is the conclusion of our work. Now, here we have prepared another catalyst that is based on cobalt aluminum hydrotolusides, and we can convert fructose to 2,5-diformylfuran. So you can take fructose and you can get the 2,5-diformylfuran using such method. So DFF, as I told you, is a useful product. The catalyst was prepared using a typical impregnation method. So we have taken metal nitrides, alkali co-precipitation followed by calcination, and we got the well-dispersed cobalt aluminum catalyst. And this catalyst were screened for this HMF to DFF reaction. So we have varied the cobalt to iron, cobalt to silica, cobalt to alumina, different ratios. And you can see that cobalt aluminum 2:1, you can get the 95% DFF yield, or cobalt aluminum 3:1 ratio, which gives 96% yield, and HMF fructose is 100% converted. HMF, suppose you want to do HMF to DFF, these are the results. If you want fructose to HMF, these are the results. So this catalyst is useful for such type of conversions. So again, this catalyst were optimized with respect to the temperature, reaction time, and solvent, and we have optimized all the parameters for preparation of this method. Again, fructose can directly convert it to DFF using cobalt aluminum catalyst. Now, it's interesting to produce something which is having optically pure, that is, we can prepare optically pure gamma valorolactone using ruthenium catalyst. So cyclization, I told you earlier, possible with levulinic acid. So biomass waste, if you do the acid treatment, or fructose with acid treatment will give you the levulinic acid. This levulinic acid with chiral ligand, that is ruthenium, THDPEN, I will give you the structure in the next few slides. This particular metal complex can give you the chiral gamma valorolactone in 99% conversion with 78 to 93% excess enantiomeric excess ratio. So this is achieved via the reaction, which is asymmetric transfer hydrogenation, or ATN. And this ATN is a very popular tool to prepare such type of reaction. So this particular product, that is optically pure GVL, finds lots of application in preparation of different types of pharmaceutical and other molecules. You can also have chiral ionic liquids using this, or you can have chiral solvents. Wherever you would like to introduce to a chirality, this type of solvents are useful. So the complexes which we have used for this conversion of levulinic acid to GVL using asymmetric transfer hydrogenation, they are listed here. So it's a ruthenium. You can see that ruthenium complex, and this is THDPN catalyst. Various forms of those catalysts were prepared, and we have done the transfer hydrogenation here. You can see that this is a chiral, and after dehydration, you get the R and S, and one of them is prominent here. So you can see that this catalyst, all the catalysts were screened, and some of them are giving better results, which were further optimized. So this is the proposed mechanism for ATH of carbonyl group. So this is the catalyst, and carbonyl group will interact, and you get the possible transition state here, how it works. Solvents are very important part whenever you are doing the chiral catalysis. So we have screened the solvents, methanol, DMF, ACN. You can see that they are giving good conversion ratios and also good EEs. Temperatures were also screened. We found that around 25 is a better conversion results and better EE ratios were obtained at this particular phase. So 24-hour, 96% conversion, enantiomer cases. Now you can see that after optimization, we can get up to 74%. So we did the ATH reaction and we have prepared the GVL in very good ratio. This is a typical concentration time profile. And what is the practical application of this particular transformation? You can convert biomass waste to chiral transformation. So fructose, levulinic acid, GVL. You can take biomass waste, levulinic acid, GVL. So you can take biomass waste related to rice husk and corn straw. This is the chiral chromatograph of racemic GVL. You can see that when this is a racemic, both the enantiomers are present in equal quantity. And when we do the reactions, you can see that we got only one enantiomer in excess, rest is in very small quantity. So this is the better way to prepare the ATH. Besides this, we have also prepared levulinic esters using ionic liquid, that is 1-methyl imidazolium hydrogen sulfate. So we can prepare this ionic liquid using this technique, and you can do the levulinic acid esterification using this ionic liquid. You can prepare such esters very easily. You can find the details in this published literature. So we have optimized this. Instead of sulfuric acid, these ionic liquids found to be useful for such type of transformation. So various types of alcohols were taken and they were esterified using this particular technique. Besides that, we have also prepared biocatalytic activities of immobilized stepsin lipase, and we have immobilized this, and using supercritical CO2 carbon, we have prepared a biodiesel using waste cooking oil. Again, this work is published in this work. You will get the more details about this. So this is the immobilization technique of the enzyme. So you can get the enzyme immobilization using this part. We are also working on carbon dioxide activation. So biomass derived products also can be obtained. So many CO2 based products can be obtained from this compound. For example, if you take aziridines and CO2, you can prepare such compounds very selectively. Then epoxide, cyclic carbonate transesterification to dimethyl carbonate, aminobenzonitriles, again cyclization here possible with CO2, and all this work using ionic liquid one can do. You can find more details in this published work. So we have immobilized this ionic liquids on resin so that they can be recyclable very well. Also, we have prepared heterogeneous amine immobilized functionalized MCM41 catalyst in which such cyclization can be possible. Then you can also prepare benzimidazoles using this carbon dioxide 6-dimethyl carbonate in between you can prepare this such type of molecule very easily using these methods. Then in last slide, we have showed you how we can prepare graphene oxide immobilized catalyst. So on graphene oxide, we have immobilized this amine, and this amine and propylene oxide can couple in presence of CO2 to produce the cyclic carbonate. So this work also we have published in ChemSystem, and this cyclic carbonate finds lots of application, and CO2 immobilization strategy one can follow using this method. So the preparation of graphene oxide based catalysis, you can take graphite using, then you can prepare graphene oxide and you do the immobilization of amines. We have also prepared ruthenium PEG400, which is a green, recyclable and reusable catalyst for construction of carbon-carbon, carbon-oxygen, carbon-nitrogen bond using CH activation strategy. So you can take this as a starting material, say typical acetophenone or other derivatives, and you can see that you can do the ortho-olefination to prepare such cyclic molecule, or N-methyl isoquinone using reaction with alkynes. Again, alkynes, you can prepare isofumarine in presence of alcohol. Here you can prepare isoquinone, and more details you will find the work published in the Green Chemistry. Besides that, as a CH activation part, we have worked on N-tosyl hydrazone directed annulation. So we can take such molecule and alkyne, and you can do the annulated product, in which you can see that this hydrogen and this nitrogen, they can be coupled with this alkyne to produce this cyclic molecule. The catalyst in this case is recyclable by some different technique. For example, this is homogeneous ruthenium PEG catalyst. So you take this catalyst, you do the reaction. After reaction, you add anti-solvent. Anti-solvent means which is not soluble into the reaction mixture. So after that, in anti-solvent, you will get your substrates and unreacted substrates and product. Your catalyst will remain in the PEG phase. So you remove that, you get the products isolated here, and the PEG catalyst can be recycled further. So although we are using homogeneous catalysis, but we can separate and recycle such type of catalyst using this technique. So this technique was further used, and you can see that we can recycle homogeneous catalyst n number of times using such type of transformation. Palladium cycle, for example, we have seen the carbonylation of Palladium cycle using aryl iodide and it is a carbonylative Suzuki coupling reaction. And we got large number of turnover number, very high turnover number for this catalyst. Besides that, we have prepared amino carbonylation of terminal alkynes. Several publications which I have done. I think due to the lack of time, I will not go into more details about this work. Some important aspect I would like to highlight. For example, here, phenol, you can put esters at para position using carbonylation technique very easily. This H can be replaced with such group R of COOR ester. Electrocatalysis also we are doing, in which you can prepare carboxylic esters from N-alkoxyamides very easily using electrocatalysis tool. So many techniques which we have developed, and we have published lots of work on CH activation. Of course, I will not go into those more details, and due to the lack of time, I would like to stop my lecture. But you can see more details about our work on sustainable aspect in this particular group, transformation and utilization of carbon dioxide. Also, you can visit our website to get more details about the work which we are doing. And with this, I would like to conclude. Before concluding, I would like to thank my supporters, that is CSIR, DST, UGC, my collaborators in Japan, for their generous support during all this work. Thank you very much.
Thank you, sir. Before that, I would like to ask that if anybody has any questions, feel free to message on the chat group. Okay, I don't, as there are no questions, I would like to propose the vote of thanks. It is an honor for me to propose a formal vote of thanks. Thank you, Professor Banage, for your wonderful insight towards the wonderful world of catalyst. and especially particular towards the catalytic reaction of biomass. We got a wonderful insight on various productions of DMF, DFF, and it's helpful to know that DMF could be produced from fructose and all, because never knew that actually biomass can be. Also, it was wonderful to know that lutetium is another dynamic element, because we had used lutetium in supercapacitor, and amazing to know that it can be used in catalysis as well. Okay, so I hope that all the participants will acquire your insight, will acquire an insightful into from your lecture, and I hope they can use whatever you said in their future works. Thank you so much, sir.
Thank you.
Sorry to keep you all waiting. There is some technical issues, so it will start soon, as soon as Tyagi sir joins. By that time, you all can fill the feedback form. please give us a little more time because the technical issues is not resolved. So give us 5 more minutes.
इसका जरूरत नहीं है ना?
नहीं उसका रेंज जरूरी फिर भी इसको ऑन रखना ओके बट द कैमरा वी हैव टू दिस आई एम नॉट टॉकिंग टू यू गॉट माय टॉक
Sir, should I share screen?
हां and cut off my talk by 10 minutes and how to change slide
Yes, I just did.
but Dr. Shetty, are you able to hear me now? Dr. Shetty, am I audible?
Yes, you are audible.
Okay, and are you able to see my slides also?
Yes, yes.
Okay, so you can start the meeting now. Sorry, I lost some time, but it was beyond our control.
No problem, sir. So now it's
Good afternoon, sir, everyone. Myself, Atul Kulkarni, would like to welcome you all for the next session of the day. It gives me an immense pleasure to introduce you. Although Dr. Tyagi needs no introduction, but for the sake of students' community, his achievements can be of great inspirational value. After completing his post-graduation from BRC Training School in the year his postdoctoral degree from the year 1991. A recipient of Max Planck Fellowship and completed research on Max Planck Institute Stuttgart. Currently, Dr. Tyagi is a career in energy conservation, chemistry in Bhagat. He is also a senior professor and dean of Functional material, nuclear material, and nanomaterial constitutes his core interest. Dr. Tyagi has more than 600 publications in reputed international journals and also authored 4 books and 1 patent to his credit. A very high H index of 61 and I-10 index of 381. Dr. Tyagi is currently guiding 10 research scholars for their doctoral and 20 students have received their doctoral degree under his able guidance. The list of prestigious accolades received by Dr. Tyagi over the past 2 decades is quite long, to name a few. He is a recipient of Gold Medal of Indian Nuclear Society in the year 2000. He was awarded with Homi Bhabha Science and Technology Award in the year 2008 that was conferred to him by Dr. APJ Abdul Kalam, former President of India. In the year 2012, he was bestowed with Professor C.N.R. Rao National Prize in Chemical Sciences. He is also a recipient of Metallurgist of the year 2017. This is a national award that was conferred to Dr. Tyagi from Ministry of Steel, Government of India. National Prize in Solid State and Metal Chemistry in the year 2018. He is a fellow of national and international science academy such as Maharashtra Academy of Sciences, National Academy of Sciences, Royal Society of Chemistry, Indian Academy of Sciences, Asia Pacific Academy of Materials. Dr. Tyagi is an honorable member of INSA National Committee of Crystallography, PhD Project Assessment Committee, Academic Council, JNU New Delhi, Board of Studies Chemical Science, HPNI. With this small introduction, I would like to invite very eminent Dr. A.K. Tyagi sir and request him to deliver a lecture on sustainable batteries. Over to you, sir.
Thank you very much for your kind words of introduction. I realize that you have an old file of my introduction. Many things have changed since then, but doesn't matter. It's always good to update. That's important. So when Dr. Shetty invited me for this conference, I was debating which talk will be most appropriate. Since this conference is on sustainable development, I thought this particular talk of mine, namely sustainable batteries and what is the role of chemistry, could be the most appropriate, and hence in view of this I selected this particular talk. And I also realized this talk I had never given for Somaiya College. Somaiya College I have been giving talk regularly for last 20 years. This particular lecture is something which you will hear for the first time. Those of you who have been hearing me in last decade or so. Change like this. Oh. So to begin with, let me show the classification of energy storage technologies. This is called as Ragond's plot. This plot is nothing but a relation between power density and energy density. I am showing you four types of energy storage systems. Capacitors, they have got high power density, but they are low in energy density. Supercapacitors are also having decent power density, but not so high energy density. Other extreme, you have got batteries and fuel cells. They have got very high energy density, but they do not have high power density. So the entire research all over the world which is going on is how to raise power density of fuel cells and batteries, and how to raise energy density of capacitor and supercapacitor. These two things are the main focus of research in not only India, elsewhere as well. This I have taken from a monumental paper from Professor John Goodenough. You may recall he got Nobel Prize in 2019, and I am very happy to share with you that 2022 is Professor Goodenough's birth centenary, and he is very much among us, and he goes to the lab in a couple of months. We will celebrate his 100th birth anniversary, and a scientist who continues to be as active as ever. So people like Professor Goodenough are big source of information. Why batteries are important? Batteries are used in consumer devices, as you can see. They are, of course, now going to be used in a big way for electric vehicles. And balancing renewable, this concept can be met by battery technologies only. Invention of battery, I thought since there could be some younger students, I will share some historical aspects. 10 cells were perhaps the first reportable and documented cells. 1856 they were designed. You can see photographs are shown here. Telegraph equipments used these cells extensively. Lead acid battery was discovered in the year 1859. And till date it is in use. Lead acid battery is yet to be phased out. Of course, you have got different chemical cells. It was the genius Professor G.N. Lewis, Gilbert N. Lewis, who first time in 1917 coined the idea that a day will come when lithium metal will be used in a big way, because he as a chemist knew lithium is lightweight and it has high density. So he was pretty sure that lithium is going to revolutionize the life of human beings. That's what happened. So the equipments, instruments which are used based on batteries, and they are taken from internet, and copyrights infringement is not intended at all. Nobel Prize of 2019, I already mentioned that Professor Goodenough got Nobel Prize for his pioneering work in metal oxides which were used as lithium intercalating cathodes. For example, LiCoO2, LiFePO4. Stanley Whittingham also shared Nobel Prize, and he discovered that metal disulfide, WS2, MOS2, etc. can be used as fascinating lithium intercalating cathodes. TiS2 also. Akira Yoshina, she showed that carbon has got tremendous scope of use as anode materials. So these three people who did pioneering work in 80s and even 70s, they got Nobel Prize of 2019. What is a battery? Battery, you all know, is a storage device which is used to store energy of a chemical reaction, and it transforms chemical energy into electrical energy. Battery can consist of two or more than two electric cells. You can connect them in series for getting higher performance. Basic building blocks of batteries are anode, cathode, and electrolyte. Electrolyte is the medium through which charge carriers travel. So these three are the main components of battery. In my group, we don't work on electrolytes, we work on anode and cathode. Different types of batteries are shown in next slide. Batteries, as you know, can be primary. Primary battery is single use. You use and dispose. Secondary batteries can be charged. You can use them many number of times as you are using lithium batteries as of now. Working principle of rechargeable battery depends on the charging process and discharging process. Have you ever wondered that even if you don't use a mobile at all, your battery is discharging by its own from 100%, next day morning you get up, it becomes 95%, then it further decreases. Because discharging process is a spontaneous reaction. It is thermodynamically favorable. It is irreversible process. You know, reversible and irreversible thermodynamics, those concepts are not part of today's talk. Whereas charging process has some barrier, and that's why you have to plug in. You have to plug in and supply electric current, and then you are forcing charging of the battery. So charging is not spontaneous, discharging is spontaneous, as you can see from these schematics also. Battery characteristics are many, of course, but the main one are its voltage, its efficiency, lifetime, electrical parameters, and capacity. These 5 parameters, according to me, are most important to call a battery better than others. What do you expect from a battery? Obviously, it should have high energy density so that it runs longer. High power density so that high energy can be extracted in a short time. And I told you in the beginning that these two properties at times don't go together. At times they become mutually exclusive. And that's where is entire research is all about. High cyclic ability, you should be able to use them for 1000 cycles, 1500, 2000, so on. You want quick charging. You want to put for charging, after 10 minutes you want to see it is completely charged. And of course, in demanding conditions, they should have safety also. Suppose temperatures of room or your climate is very high, you should be able to withstand those temperatures. And obviously, low cost also is one of the parameters. What are challenges and expectations? A battery should be affordable, long range, fast charging, and of course, slow discharging. That also you would like to use. High safety. It should be low cost, high energy density, and can we make materials which will make lifetime of your battery from present 3 to 5 years to 15 years. It should not undergo any fire, chemical leakage. Battery modeling comes into picture, thermal management, aging prediction, integrity, energy consumption. So number of things are there which one has to work on. Development of sustainable batteries as the theme of today's talk. So challenges, let us see. When I talk about anode materials, what are challenges? Challenge is that this migrating ion, lithium in case of lithium battery, sodium in case of sodium battery, they have got poor kinetics and they have got weak diffusivity. Upon intercalation, deintercalation, there is a volume change. There are severe side reactions, and dendrite formation is one of the reasons of safety compromise. You get dendrites of lithium, sodium, and as of now, they have got limited capacity also. These are the challenges, young students who are attending my talk. You can definitely do good PhD, make good career, or if you work on these kind of problems. You can use nanomaterials. Nano is everywhere. Nano can be used as a prefix to anything these days. You make nano prefix, you can make any new subject altogether. So nano is not aligned to batteries also. Nano state improves ion and electron transport by providing shorter and efficient diffusion path. You have got better reversible capacity, and they often act as cushion towards volume expansion. They have better integrity and mechanical stability, and they can also be flexible and robust. You can make hybrids. Some examples I will show. And you can have better packing density. So geometry also plays a role. one can use a material in zero-dimensional shape like this, one-dimensional rod, two-dimensional like sheet, and 3D as I show you in this figure. Each dimension has its own applications and advantage. 0D possesses unique favorable properties. 1D gets you good electrical contact, shorter diffusion paths. 2D gives you better rate capability and you can have better strain relaxation. It offers better flexibility, etc., etc. 3D offers large surface area, large electrolyte penetration, sustained structural deviation, and it provides electrical and mechanical stability. What should we do? The best course of action is to use all of them in an architectural fashion. So nano architecture comes into picture if you want to make best of 0D, 1D, 2D and 3D. You can classify anode materials into different types: insertion type, alloying type, conversion type. Probably details we discuss sometime else. Why one is bothered about lithium-ion battery? Lithium has lowest reduction potential, lighter than other elements. Most important reason, as also mentioned by G.N. Lewis in 1917, one can have shape and size variation of battery, no memory effect, and lithium has got low discharge rate. That's what you want. However, there is a big problem. Lithium's abundance is highly skewed. Lithium is present only in a couple of countries. In India, we don't have much of lithium. And that's where comes geopolitical issues which a country can be subjected. There is a functioning of battery, how they work, intercalation, deintercalation, okay. You can see cathode, you can see anode. Anode is graphite, cathode is transition metal oxide. Discharge process is lithium ion becoming lithium metal. Charge process is lithium ion becoming lithium metal. Lithium atom becoming lithium metal. And this is compared to rocking chair. You sit on rocking chair, it moves back and forth. So this way only this comparison has been drawn towards the functioning of lithium ion battery materials. The characteristics of electrodes are: lithium ion should be able to do intercalation, deintercalation with cathode anode. The process should be reversible. They should have structure of intercalant, intercalated compounds, similar structure. Volume variation should not be very high. It is volume variation which often creates a problem in this kind of energy storage materials. Chemistry has played a big role. You see number of anodes: silicon, lithium, composites, graphite, lithium titanium oxide. Number of anodes, number of cathodes you see: lithium manganese oxide, cobalt oxide, lithium iron phosphate, etc., etc. So a lot of cathode and anodes have been discovered. All has come because of the concepts of crystallography and concepts of chemistry. We have been, so this was in general. Now very quickly I will show some example from my group and then we have discussion. In my group we have been developing lithium iron phosphate based cathode materials, and you can see from XRD pattern they were well characterized, and we use a range of lithium and iron. They were very well characterized by different techniques, as you can see here, and by Moss bar spectroscopy also they were characterized. By Moss bar you can find out how much iron is present in 2+ state and how much is present in 3+ state. Based on that, one can work out in final product what is the amount of LiFePO4. LiFePO4 is the active component of cathode. Rest all muck is inactive. FeP is inactive. Of course, FeP provides you some conductivity benefit. So we found that if ratio of lithium and iron is 1.05 to 1, you get the best performance, because in this compound the larger part of circle corresponds to LiFePO4, which is a nice cathode material. So different techniques were used, impedance spectroscopy was used, and battery cyclability was investigated by using different techniques. We also have worked on MOS2 for simple reason. MOS2 has got a layered structure. Layered structure have added advantage of having interplanar spacing in which lithium ions can move in and out. And all these materials were prepared by very simple chemistry, by using test tube and beaker kind of facilities were used. And here is the result. We have investigated them by X-ray absorption, near-edge spectroscopy. By this, we could propose a mechanism how MOS2 becomes LiX MOS2. Upon further lithiation, this changes, it becomes MO. We have proved this by Zanes and EXAFS. These techniques are available in Raja Ramanna Center for Advanced Technology, Indore. And as you can see, a detailed mechanism of intercalation and deintercalation was proposed as part of this work. So, for this part of the work, I would conclude by saying that at lower pH, strongly coupled composites of MOS2 and CNT could be synthesized. Why coupling was strong? Because at this pH, one of them has got positive charge, surface charge, and other one has got negative surface charge. So because of different charges on surface of MOS2 and CNT, there is a very nice blending because of electrostatic attraction. This composite was found to be an excellent candidate for fast electron transfer, excellent structural stability, and we also proved that only 8% carbon is sufficient to improve the performance of battery, because carbon provides electronic conductivity. Likewise, of course, we worked on MO2C anchored on graphene, as you can see in this. Details probably I'm going to escape. MO2C anchored on graphene sheet was used as anode in lithium batteries. As you can see, the important result is there that we got high capacity, and it was having some superior properties compared to others, and its adverse tests also it could tolerate. It was subjected to highly adverse tests and it did not crumble. This is the advantage of having this kind of nice chemistry. In summary, I would say MO2C composite has been synthesized by a very simple method, and phase purity was confirmed by XRD. Detailed cyclic voltammetry study elucidated the redox and capacitive behavior. 5% of this carbon component is sufficient to show superior properties, and we made a full coin cell. We showed 120 milliamps hour per gram at 50 milliamp per gram kind of capacity. Next generation lithium sulfur batteries also have been developed, as you can see in this slide. Here we have used graphite, LiCuO2 as cathode, graphite as anode. Surface is sulfur also has been used, and some properties I have shown you here. There are a number of challenges. Sulfur has got low conductivity, as you know from the basic knowledge of chemistry. So our strategy was to encapsulate it into various carbon matrices. Then of course it undergoes shuttle effect. So we can use porous carbon, we can use York shell, what you get in egg shell. This kind of microstructure provides enough cushion for absorbing metal oxide nanostructure induced what you call strain. You can wrap sulfur by conducting polymer. So sulfur is there and conducting polymer can be encapsulated. We tried different types of approaches, and here I will show you one of them wherein sulfur was coated by highly conducting polypropylene. In result, we got improved conductivity, and this polypropylene PPY also acted as a cushion towards strain absorbing, and it provided the ability to absorb the polysulfide intermediate, though this degradates in between. So all these intermediates could be absorbed, and this configuration was well characterized, and we used it almost for 2000 cycles without appreciable degradation. So from lithium battery, I moved to sodium battery. As I mentioned the beginning itself, that lithium problem is there. Its abundance is very skewed. whereas sodium is found everywhere. Lithium is predominant. Half the lithium of the world is found in Chile, Australia. Then remaining half is Australia, Argentina. China has some lithium, and other countries. Our share is very small, whereas sodium is found everywhere. So this kind of geopolitical irregularity can lead to a lot of issues, including price war. International price wars are made out of this kind of undue advantage which nature has given to a given country. So comparison wise, if you see, you have got for sodium batteries, advantage is low cost and greater safety. Sodium is less reactive compared to lithium. Its disadvantages are it has got low energy density and low cyclic rate, as you can see in this slide. So this is the typical schematic of sodium and battery cells. We have got NaPF6 as the electrolyte. We have got carbon as the anode, and NaCO2 is used as cathode. In my group, we have made, my colleagues, younger colleagues have made all types of compounds. They have made anodes based on biomass. They have made glassy anodes. And our students and colleagues have made cathode materials like based on polyanion, glass ceramic, etc., etc. So in this case, what we found, graphite, which was used quite extensively for lithium batteries as anode material, does not work very well for cathode materials. For cathode materials, for anode materials in sodium and battery, it does not work. In this case, we have developed hard carbon. Hard carbon has got slightly larger interplane spacing compared to graphite, and that's one reason that large sized sodium ion can move in and out compared to in graphite. So simple protocols are shown here. By using kitchen waste, one can make this kind of beautiful hard carbon. This was made by lychee seeds. Lychee seeds were available in kitchen. You do pyrolysis as shown here, and you get highly porous hard carbon as shown by this microstructure. These batteries were fabricated and they were well characterized, as you can see here. And this is a protocol for making a battery. You start with solid, do coating using Dr. Blade, then do calendering, drying, cell manufacturing, coin cell. You can also make pouch cell, and a patent was secured by our colleagues in collaboration with IIT Bombay, as you can see in this slide. One can also substitute heteroatom. Carbon is all carbon. You can put nitrogen, boron, oxygen, sulfur, phosphorus. In our case, we selected sulfur because sulfur has got high polarizability, which supports high ionic conductivity. And in this case also, a full cell was synthesized by using sulfur doped hard carbon. These are the advantages, as you can see in this slide. These are the polyanions which have been used. This kind of polyanions have got corner sharing polyhedra. In this case, the lattice has got lot of free volume. So they have got, in simple language, somewhat low packing fraction. Low packing fraction ensures you high free volume. And higher the free volume, better is the ionic conductivity. That's why they are far superior. Recently, a paper of our colleagues, me and my colleagues, got published in Electrochemica Acta, which is a benchmark journal, on this compound, wherein some oxygen was changed by fluorine. These are the summary of our work on sodium-ion batteries. These are the reports of Sumitomo, Sharp, Faradion, Sharp. These are the combinations of cathode. All of us used hard carbon as anode. These are the capacities: 650, 153, 126, 90, etc., etc. In our case, we developed this much superior cathode, and we made a much superior hard carbon by using kitchen waste. And you can see our coin cell after sulfur doping has got 244 watt-hour per gram kind of capacity, which is better than many from international giants, whereas our chemistry definitely proved out to be much better. Future research scope in case of battery materials, in case of sustainable battery materials, is that you have to develop advanced anode materials for lithium and sodium ions, and that's where comes your knowledge of chemistry, your knowledge of crystallography. One has to develop advanced electrolytes that can enable better battery performance in terms of high charge and low discharge rates over wide temperature range. Long cycle life you would always prefer, and here again I would say once again, your sound knowledge of crystallography plays a big role. Next generation batteries will be metal free. They will not use any metal. This is a kind of advantage. And in BARC, we are also working on what is called as nuclear batteries. They are different concept altogether. In today's talk, I'm not going to cover, but sometime we'll discuss at length. These are some of our contributions in terms of visuals. This is a coin cell made by our colleagues, pouch cell, this powder, and this NMC powder, and it could be converted to coin cell. This work has been transferred, this know-how has been transferred to 4 private parties, as you can see here. This technology has been transferred to giants, Tata Chemicals in Pune. So they are going to scale up all these compounds in near future. This is a battery lab in our group at BRC. Please come anytime. I look forward to show you this battery lab. At last, I would say we don't inherit the earth from our ancestors. We borrow it from our children. David Brower said that. So that's where comes the concept of sustainable development. You have to bother about this. I will acknowledge my number of colleagues and students. Dr. Kruti Halankar is sitting right 2.5 feet from me. A very bright student. She did PhD with me a couple of months back. She completed. Whatever work today I discussed, a lot was done by her. And in another 2 weeks, she is flying to Germany for postdoc. Dr. Deepa Datta Pathak, Balaji Mandal, Dr. Dimple Datta, organizing committee. Some photographs I took from internet, and I may once again give a disclaimer that no copyrights infringement was intended, either knowingly or unknowingly. I must thank personally Dr. Sugandha Shetty for always inviting me in conference organized by KJ Somaiya College, and I always like to interact with all the colleagues at KJS. With this, I conclude my talk, and now I will appear on the camera so that we can take up some question and see each other face to face. Yes. Yes, conference organizers, you can continue. You can invite questions.
Thank you, sir. Thank you, sir, for the kind lecture. Is anyone having questions? Can feel free to drop on the chat box, please. One question. Lithium-ion batteries.
Explode with fire.
Yes, yes, sir. There are number of issues. See, why lithium batteries at one time, 5 years back, it was a national news, in fact. See, what is happening, there are 2 reasons because of which batteries undergo fire. One reason is the formation of dendrites. Dendrites are needle-shaped form of lithium metal, and it provides short circuiting. If you are short circuiting in any electrical device, it may lead to spark, it may lead to fire, etc., etc. Another reason was that these battery materials use sealant, and at times sealant materials also have issues. So for these 2 reasons, mainly there was some fire in place of batteries.
Any other questions?
And if anybody wants, they can ask me a question by email also. So please share my email address with them.
Sure, sir. Sure, sir.
Okay, so if there is no other question, should I disconnect?
Yes.
I would like to propose the vote of thanks, sir. I would like to propose a formal vote of thanks. Thank you, sir. Thank you for contributing for the importance of benefits of their thanks to increase right of the guidance. Thank you, sir. Now we shall have a short break of tea and we will assemble for the next session at 3:30 p.m. Thank you.
कोण हॅलो आता सगळ्यांना जगाला ऐकायला येणार. हॅलो सर.
Good afternoon, everyone. Myself, Shraddha Deshmukh, would like to welcome and introduce our renowned speaker, Dr. Nitin Lapsepwar. He has completed his MSc in 1986 and PhD in 1990 from Dr. H.S. Gaur Central University, Sagar, Madhya Pradesh. Currently, he is the Chief Scientist and Head of Energy and Resource Management Division, CSIR Navy. He has 35 years of research experience in environmental and energy-related research. He has worked as STA and JSPS Fellow and visiting overseas researcher at NIMS Tsukuba, Japan, and as a visiting professor at Kyushu University, Japan, under Global COE program. He has also worked at other international laboratories on development of material and processes, including low-cost and nanomaterial catalysts for their applications in GHG emission control, automobile emission control, including diesel soot oxidation, cleaner energy generation, and climate change, etc. He has over 175 research publications with over 6,800 citations, an H index of 44, an I-10 index of 104, and 22 international patents, in addition to a few contribution inputs. He is an identified expert in Central Pollution Control Board of India in the area of air pollution control, vehicular emission, and also contribute as an expert to several other national and international agencies. His research contributions are recognized through various awards, including Maastricht Award 2020. With this short introduction, I would like to welcome Dr. Nitin Lapsepwar, sir, to deliver his lecture on materials and processes for cleaner energy and environmental application.
Very good afternoon, and thank you very much for the kind words. Can you hear me?
Yes, sir.
Okay, I'm trying to share my slide, so please confirm if you are able to see the slide.
Yes, sir.
You can see the slide? Can you please confirm?
Yes, sir, it is visible.
Okay, thank you very much. And in next about 45 minutes, I'll brief you about some of our research activities and how it is relevant to both energy and environment with the background of chemistry and materials, of course. So this is how I plan today's talk, so that I can give you an overview of the things, and if there are youngsters, I can possibly encourage them with the kind of trends going on in R&D in the domains we are dealing with. So we'll quickly look into the energy scenario and energy environment nexus, the so-called energy environment nexus we call it, and then how best chemistry and materials can contribute. And then we'll take two topics, specific two topics. One is related to the carbon capture or CO2 capture, which is a hot topic today through chemical looping combustion. And second is catalytic diesel exhaust emission control, which is again pretty much of importance as far as India and many other countries are concerned. And we'll look for some cleaner energy related applications. So I'm sure you must have got the background from my previous speakers about the NEERI. To save time, I would say that please go through the website of CSI and NEERI. And if you want any additional information of a particular topic, please don't hesitate to get in touch with us, and we'll be more than glad to provide you the information. This is the department or division I lead. We call it Energy and Resource Management Division. So as far as the mandate of this division is concerned, we are into mostly environmental aspects of energy, okay, and then the resource management. So per se cleaner energy, and in my next slides, I'm going to explain you that what are the major aspects of energy, okay. So the diesel emission control, I'm going to take with more details. Then we also work on some hardcore like material science, like shape control catalysts. And the second thing I mentioned to you is a chemical looping combustion. So we are developing oxygen carrier materials for this application. A colleague of mine works on the fuel cell. I'm not going to cover today. Then we have some specific environmental applications which are not related to chemistry. So I'm going to skip these things. Like we do work a lot on improved cook stove, but to give you a quick account that probably the air pollution burden or health burden from cook stove is more than any other sources, including the automobile. So luckily or fortunately, Government of India has been addressing it through LPG penetration, but there is a lot to be done still. Then we work on the small combustion devices like tandoor and incinerators. Like being an environmental engineering institute, we work on the biomedical waste incinerator, sanitary pad incinerator, and so on. I also work on the transport emission management, okay, and then catalytic CO2 reforming and energy management, and a couple of other things related to applications of drone, AI/ML, and sensor for environmental monitoring. So you can again go through the web page and let me know if you are interested in something else. So sustainable development, I'm sure somebody must have explained one very simple definition of sustainable development. And yes, at the outset, let me apologize that there will be quite a few content in my lecture, which is meant for students and young faculty. And those who are having probably more experience than me, please ignore and please don't feel offended. It is for the benefit of that and sometimes to pitch in the background. So meeting the needs of the present generation without compromising the ability of future generation is what is known as a sustainable development. One very simple example is, say, for example, we are using a fossil fuel energy, no problem. We have got energy, we are using it for our generation. As long as we were releasing the CO2, which was, I would say, within the assimilative capacity of nature, we were not jeopardizing the future of the future generation, okay? But since we are exceeding the limit of CO2, which is acceptable by the nature or the climate, we are affecting our future generation through climate change. Similarly for water, so there is enough water, and if you are using the water, every year it gets replenished. But if you are using excessive water and depleting the sources of water for future generation, that is not sustainable. It's a very, very simple word, okay? But to find out what is sustainable and what is not sustainable is not a simple task. Okay. Nowadays, LCA or life cycle assessment is a very common tool. Okay, because we need to understand that sometimes what we perceive is really not the overall footprint of any product, because we just see and we calculate the materials, or for example, in a power plant, we calculate how much of coal is going inside, how much of power generation is there. And then we will simply calculate that 1 ton of coal is equivalent to this much of CO2 and thus the footprint. While that's actually a small portion of the footprint, because we normally don't consider, like how the coal is mined, how the coal is transported, how the power plant is built, how it is maintained. Okay, what is the life of the power plant, how the fly ash is generated, how it is, like disposed of. All that put together makes a pretty huge environmental footprint. Okay, and nowadays, today we talk too much about the GHG footprint or the carbon footprint, but we should not forget the other footprints. Other quick example for the students is like LPG, and I remember we used to calculate that 1 cylinder of LPG with say 10 kg of like propane, how much of CO2 it will generate. So we used to write the formula: propane plus O2 is equal to this much of CO2. But that's not the actual footprint, because its footprint starts from extracting the crude oil, which requires a lot of energy, transporting the crude oil, for example, from Saudi Arabia to India by ship. That requires a lot of energy and a lot of fuel. That has its own footprint. It comes to the refinery. Refinery processes consume a lot of energy. They generate a lot of emissions. Everything is taken care. Then from there, it comes to your city, to the bottling plant, to the cylinder, and then cylinder is transported to your, like service center, and from there, the dealer, from there it is coming to your flat scheme, and there they are using your, like even the elevator or lift. Everything should be accounted for as far as energy or material inputs is going in the LPG. So the life cycle assessment, and then comes the disposal related problem. So LCA is absolutely essential to work out what is sustainable, what is not sustainable, and to quantify the actual, like the footprint. This is another I picked up from some literature that we feel that the emissions from an automobile comes from the tailpipe. That's what we know, that exhaust pipe releases the emission, including the CO2, carbon monoxide, hydrocarbon, and the particulate matter. So first, this orange circle shows where people think emissions from driving come from, while on your right, where emissions from driving actually come from. Disposal of car, significant emission. Tailpipe, yes, it is important, but that's not the only thing. Then there will be emissions from the tires, brake, then the electricity used in the manufacturing of this thing, the making of the car, processing, raw material, and so on. So life cycle analysis and life cycle assessment is extremely important to work out, okay, whether it is sustainable or how green it is. Now we also use a lot of words like green technology, sustainable engineering, and I was very happy to see the galaxy of experts talking on this domain. But again, there is also, I've attended a couple of lectures and we miss a few things, okay? Because generally nothing can be absolutely green, okay? It's very difficult. So it is generally how green. So what we try to do in the green chemistry or any other things, we try to reduce the footprint and reduce the resources, okay? So green synthesis, for example, replacing organic solvent is very common with the water. That is relatively green, because if your temperature is 120 degrees Celsius, the process you have made green in terms of using water instead of organic solvent. But how about using that energy for 150 or 120 degrees Celsius? Where from it is coming? If it is coming from, like coal-based power plant, there is a footprint of CO2, okay? There is a water footprint. If you are wasting something, some wastewater, how to treat it? There is a footprint. From where you are getting these chemicals? There will be some raw material, there will be some mining, refining, and then packing and transportation to your lab. So nothing can be called absolutely green. So in the green technology or sustainable engineering, we are trying to reduce the footprint of this thing, okay, by any means. So minimum and smart or judicious use of resources is very important. use of sustainable or renewable sources. For example, instead of using electricity from a power plant, if you have some other ways to use it, say solar energy, that is always better. Green building, for example, okay, so it's basically minimizing footprint. If you have seen some green building, you can't say that the footprint was zero. No, they use some glasses, they use some amount of cement, okay, and for production of that cement, we have used energy, we have created environmental pollution. The only thing is, now we have set a standard that is meeting, that building is meeting that standard to minimize the footprint, okay. Similarly, green lifestyle, which I believe is most important. If you try to reduce your footprint, nature fortunately has got a huge assimilative capacity or repair capacity or regeneration capacity. You can possibly emit huge amount of CO2, okay, which nature can take care of it through photosynthesis to natural processes, okay. But what we are trying to do is to compete with the nature that, okay, if you can assimilate these many gigatons, I'll try to emit more. If you're trying to take care of the CO2 through photosynthesis, I'll try to cut down the tree. Okay, so that's the way actually. So we have got enough limit if you work sensibly. Okay, so just to recap, both are relative terms and it is also contextual. Okay, sometimes we say, why don't you eat the local fruit? Because the transportation related footprint can be reduced and it will be fresh. It will not be frozen. Okay, so these like the life cycle assessment database is very specific or very contextual. Something which is having some footprint in India is different in other countries. Okay, so minimizing the waste is one of the most important things. So the message is every process and product needs to be looked into with LCA approach, green technology and sustainability approach. Okay, and every requirement or need to be looked into the food, space, energy with this approach. Now, this is becoming a big area. So who all can contribute? And you must have kind of got by now that practically everything has got a footprint, environmental footprint, energy footprint. Okay, so naturally everything. Somebody is in cement manufacturing, somebody is in architecture, somebody is like data scientist, somebody is chemist, biologist, geologist. Everybody can contribute because they are involved in something which they can try to sort of reduce the footprint of. Okay, so just saying this thing that whatever your discipline is, you can always contribute to these kind of a broad topic of sustainable engineering or green engineering. On the contrary, these are all highly interdisciplinary areas and you should collaborate and work on it. Now, coming to the energy and environment nexus, okay. So air pollution, we all understand completely from energy, okay. But the energy related air pollution, conventionally, we talk about the emissions of nitrogen oxides or sulfur dioxides or some particulate matter or the fly ash. Today, we are talking too much about the CO2, which is of course required, but we should also talk about these conventional pollutants, which are also on a higher side, okay? And then we should talk about the energy conservation, energy management and all that. A significant footprint comes from the waste disposal, okay? And significant health, I would say, damage, okay, comes from the waste disposal, which needs to be taken care. Okay, now this is the changes in the primary energy demand by fuel and reason. Okay, so you would see that there's a decline in the European Union and the United States. So one of the reasons is, yes, they have made good efforts to like stabilize it. But we need to also understand that already their per capita energy consumption is very high. Okay, so in a way it's good beginning, but their benchmark is pretty high. India, obviously, we know is one of the most fast growing country, not only in terms of the economy, but in terms of the energy consumption as well. But we need to also accept that our per capita energy consumption is quite low. That's number one. And the kind of efforts India is making towards greening of its energy is second thing, which is very impressive. If you're not from this domain of energy, you will read quite conflicting news articles. For example, our coal import is rising. In fact, today in Maharashtra and many parts of the country, we are facing the electricity or power shortage. And we are trying to increase the coal demand. that looks very conflicting with the kind of programs we have, the kind of future we have, and the kind of things we are talking about, the net zero and other things, okay, by 2070. But it's very realistic. And unless we address this thing, okay, we can't divert, okay, we can't ignore these things. Like one day you read, it's very impressive. So what is actually all about this? If you do not understand, if you understand, please ignore me. First of all, 20 years ago, when I was young, in fact, and 30 years ago, energy means providing electricity to the rural home. If somebody asks some sensible person that what do you want to do in terms of energy, he will say, okay, I want to take care of the load shedding in the rural areas. 8 ghante, 10 ghante light jati and people are, troubled like anything, and the farmers do not have electricity for pumping the water and all these things. But today, energy symbolizes pollution, like greenhouse gases, the climate change, the health impact, okay, regional conflicts. You have seen many times, right from the Iraq war to today Ukraine war, what is happening, why, how the countries are blaming each other. And we can read a very smart statement from our external affairs minister, okay, and Europe is trying like anything to reduce the gas supply from Russia. Economic jerks, last 1 month, you know how much price of the petrol and diesel has gone up, okay, strategic planning. So energy is no more like just take care of the electricity, provide electricity to the poor and provide electricity to the rural home. It is something to do by a never before catastrophe in terms of the environment, number one, the regional conflicts, and there are wars because of the energy, the country's economic jerk, which is very, very important, so is the strategic planning. Okay, so energy is such a domain, and that's why we should invest a lot of R&D efforts when it comes to the cleaner energy, when it comes to the energy which India can rely upon, because it's no more like only energy, it's a strategic. Okay, that's the reason we don't want to spoil our relation with certain countries. Now, energy, this is the energy outlook. If you are having any confusion that within 10 years, there won't be any petrol and the diesel and everything will be solar and the battery and the hydrogen and all that, or the wind or the nuclear, no, we are wrong, okay? There will be a transition, there will be a lot of development as far as renewable is concerned, but it will take its own time, okay? We cannot switch on to that because it's not easy to generate despite the fact that India has been one of the most impressive countries. So on your right side, you can see some graphs, okay? So the red line is, it's business as usual. So if you don't do anything for renewable or cleaner energy, okay, it will shoot like anything. Then evolving transition, the less globalization and rapid transition. Rapid transition means aggressively we need to address this. On your left, you can see some bar diagram in which green is oil and then the gas and then the coal. So even in 2040, okay, which is almost 18 years from now, you can see there will be significant amount of fossil fuel based energy sources will be used, okay? And that's for a simple reason that, for example, if you have today 100 plus gigawatt renewable energy generation, you would expect in next say 8 years by 2030, we will touch this figure to 500 gigawatt and we will stop using the oil, okay? Unfortunately not. Why? Because by the time your energy demand will also increase almost twofold. We are growing. So whatever addition of renewable is happening, that will get compensated by the addition of, you know, like energy requirement. Okay. So it's a very simple scenario, but then what India is doing probably is the best we can do. Okay. So it's not like, for example, you will get some states like statistics like global emission from power sector increased by 5%. Despite the fact that most of the countries are trying to go for renewables. Majority of the global electricity demand growth was met by renewable energy, 57%, and 43% met by coal. What does it mean? You have an additional 100 gigawatt demand. You are trying your best to meet from renewable energy, but more or less half you can meet. So you need to even increase your coal consumption, unfortunately. Okay, so that's the way. So what is the lesson before we go into the things? Fossil fuel consumption is likely to increase during the next 2 to 3 decades, mainly due to the enhanced demand. Practically no assimilative capacity left for air pollution, okay? And there will be two fundamental aspects. One is the greenhouse gas emissions and conventional pollution. Okay. Now there are three aspects of energy. How to reduce the overall footprint of energy. One is the energy generation, which we all understand and we talk, always discuss, and people are doing and countries are doing very impressive work. We have to go for the cleaner energy like renewables, which should be overall clean, it should be efficient, it should be cost effective, and it should be sustainable. The second aspect is energy use. Okay. So energy use means it should be efficient with minimum footprint. So generation of energy is one thing. Okay. For example, it is coming from coal or it is coming from your solar panel. Using it for 1-star AC and using it for 5-star AC is what is called energy use. Okay. So we should use with the maximum efficiency. So efficiency is a buzzword when it comes to the energy generation, transmission, or even use. We should understand this very clearly. Then energy demand, efficiency, there's a lot of work going on. We are also doing, my colleagues, they work on the AI tools and the ML tools in that. There are concepts like integrated industrial energy management, okay, or integrated industrial energy and sustainability management, because all these things are linked to each other. If you are very good in using the electricity, we are very efficient, but we are not efficient per se in using the water or the resources, and we throw the food and all these things. That doesn't really effectively contribute towards the environment. And that's why they call it integrated industrial energy management or sustainability management. It should come from all the kind of domain or all the sectors. Okay. Now, I think, yes, we are still left with about 20 minutes. I will quickly take up these two applications wherein we are using the use of the material or the chemistry. One is a chemical looping combustion. So one thing is very clear. We are going to use coal. The best thing is how clean we can use this coal in a way. So clean coal technology is one of the important program of Government of India. Okay. So we need to say gasify the coal or sort of C2L like coal to liquid, or we need to go for the carbon capture and utilization. So why, I'm sure somebody must have explained you why there's a need of carbon capture. Sequestration we know, okay, because there'll be too much of CO2 and we can't avoid it because our energy demand is going up. So we are going to use the fossil fuel, we are going to use the coal for next 10 years or 20 years or so, or even more than that. So we need to do something with the CO2. So the first problem is the CO2 coming out of a power plant is in the range of say 12 to 15%. And you can't use this CO2 directly for any applications. Okay, so first we need to pre-concentrate it or separate it and make it something like 90–95%. Okay, so for that, what is known as a CO2 capture. So CO2 capture is generally done through the adsorption or absorption. Okay, so TSA, PSA processes. This process is a competitive process to the adsorption and absorption. Okay, what is done here? You can easily understand that CO2 is diluted in the exhaust. Okay, why? Because we are combusting the coal with air, and air contains 78% of nitrogen. So this nitrogen is there in the exhaust also, because oxygen is consumed for combustion. This nitrogen is there. So because of this nitrogen, the CO2 is available only in 12 to 15%. Suppose instead of air, you are using pure oxygen. So you are burning coal, which is carbon, with the pure oxygen. So you will get pure CO2. Or if you are using methane per se and using a pure oxygen, okay, what you will get is a CO2 plus water. Water can be condensed and you can get close to pure CO2. That is known as oxy-fuel combustion. But all of us understand that it's not easy and cost effective to generate so much amount of oxygen. We didn't have oxygen even during the COVID pandemic. You can imagine the kind of oxygen will be required for power plant. So there is a process in which metal oxides are used. So these metal oxides are they act like oxygen carrier. Okay. So the reaction will be between say methane plus metal oxide. And at high temperature, this methane will react with the oxygen which is available in the metal oxide. It will form the CO2 and the water. Okay. And the metal oxide will get reduced to metal. and this metal will be reoxidized in air. Okay. Metal to metal oxide reaction is exothermic reaction, we all know, and the actual energy comes from this regeneration cycle. Okay, so this is known as a chemical looping combustion. So it's still at the stage of infancy, and there are a couple of pilot plants, especially in the Europe. Okay, so oxygen carrier or metal oxide is one of the key for the success of this chemical looping combustion CLC system, which should have these kind of properties. Okay, and like for example, if you are using copper oxide, which is a good oxygen carrier, so at high temperature, this process is I would say thermodynamically feasible at about 850 degrees Celsius. So you are using copper oxide particle. After reduction, it will turn copper particle, and they will start becoming soft and start melting at high temperature, and they will form lump. Okay, so it cannot be used like that. So it has to be supported on some support like high temperature, stable alumina, or thermally stable alumina. So these are some of the common compositions. The most common probably the nickel oxide, which is extensively used. So nickel oxide, nickel couple, which gives you about half a mole. Okay, supported on alumina is one of the best material studied so far. Okay, so these are the oxygen carrying capacity. These are the different combination, redox combination, in which we can use these materials to provide oxygen for the combustion of your fuel, like methane. So there is quite a critical, or I would say tough criteria for selection of these materials. They should comply to many, criteria. They should be thermally stable. The fluidizability should be good. Obviously, they should be low cost. They should be environmentally benign, as we all know. They should lose the oxygen. Okay, they should give a good CO2 selectivity. Otherwise, carbon monoxide can be formed. So these are the things. We were actually working on a catalyst for soot oxidation and other applications, and suddenly we realized while exploring its redox properties through TPD, TPR studies, okay, where temperature programmed desorption of oxygen and temperature programmed reduction, we realized that possibly this compound can be used for oxygen carrier. And one of the reasons for this was that the copper Mn, if you are reducing, it doesn't get completely reduced to say copper and Mn metal. Copper oxide will get to copper, but the Mn oxide will be stable at MnO form. So you're basically compromising on a little bit of oxygen property, oxygen capacity, but this thermodynamically stable MnO provides kind of a support. So the advantage with these kind of a material is, like in case of nickel oxide, I explained you that you have to use the alumina. Here we can call it a self-supported. We don't need alumina. So if you have 25% nickel oxide and 75% alumina, your oxygen is coming only from nickel oxide. While in this case, it is 100% copper Mn. So it will give you a lot of oxygen carrying capacity. So these were the theoretical advantages we worked out, and then we were looked into the delta H, delta S, and delta G data for this, and we thought this compound should work. So we did a simple co-precipitation synthesis, and we have done then CLC evaluation. So CLC evaluations can be done using a fixed bed catalytic reactor, or like steady state material evaluation assembly. It should have some mass flow controller, a GC coupled with the reactor, quartz reactor, Anchorel reactor, and some precise control over the temperature and other things. So this is how you generate this is the characterization data about the oxygen TPD and H2 TPR, which tells you how much of oxygen can be dissolved, or what is the redox properties of these materials. And then, of course, you need to do the typical XRD and other things, typical characterization to understand the purity of phase and all those things. After that, we do the CLC evaluations, and we generate these kind of a curve. So what you precisely do, you keep your material in a reactor, you pass the dilute methane, okay, and then you heat it at, and you stabilize it at about 800 degrees Celsius. So methane will react with your metal oxide, the oxygen content of your metal oxide, and will form CO2. And this CO2 can be measured simply by GC or any other technique, IR-based technique. So that's how you can create a graph that your, say, 1 gram of material is able to combust how much ml of methane with what concentration. Okay, and then the next job is how to regenerate this material. So we can like have the multi-cycle CLC evaluation. After that, you can quickly cross-check whether your material is deteriorated or it is stable for multi-cycle. Okay, so fortunately, this material was stable. Then we worked on the scientific aspects, or I would say academic or theoretical aspects, wherein we developed mechanistics aspects, that what is basically happening, how the material is getting regenerated. So this is probably the one of the first materials simultaneously reported by us and the Swedish lab independently, wherein we proposed a mixed oxide based material. Otherwise, so far it was only single metal oxide supported on alumina. So this has got interesting kind of reviews. So these were the silent finding. And then we became a little more ambitious. So instead of copper, we used iron, for obvious reason that iron is low cost, iron is environmentally much safer and all that. And fortunately for FeMnO3 also, we got the similar results. I'm not going to repeat it. There are publications on this. Now, how to move forward? Frankly speaking, as a chemist and material scientist, we have already done our job. And now we are looking forward to try to scale up this synthesis to kg level, okay, or kg scale, and try to collaborate with somebody who is comfortable with the fluidized bed experiments, because this is like high temperature applications, and fluidized bed, there are only few researchers, I would say, who work on these kind of applications in our country. So we are trying to collaborate with the IIP, Dehradun and IIT Kanpur for upscaling this work. Okay, so I'll stop here as far as this application is concerned. And in the next 10 to 12 minutes, we will look into another interesting applications which we are working with a lot of application of chemistry and catalysis. As I mentioned, it's not only the question of cleaner energy generation. The cleaner energy use also can sort of slow down the process of pollution or process of climate change. One very simple example which we are experiencing every day is, for example, Euro 6 norms or Euro 4 norms, okay, because the vehicle are becoming more cleaner. So this is the second aspect, the cleaner energy generation, like the solar we are generating, or the wind we are generating, wind energy. The second very important aspect is a cleaner energy use, which often we are ignorant of, okay, but not the government and the scientific community. How to reduce the footprint of these energy sources. For example, diesel. So there can be a vehicle which is Euro 6 compliant, and there can be a vehicle which is Euro 2 compliant. So the difference is the Euro 6 vehicle for the same amount of diesel, say 1 liter, will emit minimum pollution load. Okay. The same vehicle, if it is very efficient, will also emit less amount of CO2. So that's precisely reducing the footprint of energy use. Okay. So we are also working on this domain. Mostly for automobile applications, this area is dominated by noble metal catalyst, because there are many advantages of noble metal catalysts. Their activity, their low temperature, light off temperature, okay, their chemical stability, everything is in favor of catalytic applications under even harsh conditions of automobile. Why I'm calling harsh? Because the temperature can fluctuate from say 150 degrees Celsius to 700-800 degrees Celsius very quickly, and it keeps on fluctuating. The composition of exhaust which you need to treat can vary. The volume of exhaust is so much you can't imagine. It can be like 10 to 200 liters per minute, okay, or even higher than that, much higher than that. So the conventional catalysts are mostly made of noble metal catalyst, okay, and there are two approaches, because the noble metals are scary, okay, and then they are very costly, because they are used in multiple catalytic applications and even in the jewelry and other applications. So there are very limited resources of these precious metals. So there have been extensive efforts. First is to reduce the amount of noble metal. Say you are using say 20 grams per cubic feet or 50 grams per cubic feet. How to reduce the amount of platinum with the same amount of activity? And there have been excellent work on this. The second is, can we replace these noble metals with non-noble metals or mixed oxides? Okay, that's the second approach. We are working more or less on both the approach. In the first approach, we did some interesting work wherein, with a colleague of mine, Dr. Sarunan, we tried to prepare these kind of hollow structures. Because in catalysis, we understand that if you have this kind of a ball, okay, only the external surfaces of our use, because catalysis is a like surface phenomena. What is inside of the bulk, we call it a dead volume, obviously, okay, because that is not being used. It's only the surface. So unfortunately, these particles are already very small. So it is very complicated to make the hollow structures, but there are methods, okay, you can refer to the application of these publications. So it is possible to prepare this hollow structure so that we are trying to reduce the dead volume. Okay, it's like a football, okay, wherein you can have pores and the surface is, of course, accessible. The problem is the structure stability of these compounds, okay, because these structures are pretty hollow. And if you were to heat it at 800 degrees Celsius and frequently cool it down, those may not be stable. But still, these kind of approaches are very interesting and important for low temperature applications. For example, VOC's oxidation is a growing area. So VOC's oxidation can be achieved at say 150 to 250 degrees Celsius, wherein these kind of a structure would be stable. So this is the approach number one, wherein we are trying to reduce the amount of platinum. And there have been very good publications and patents, mostly by the academic as well as industry, wherein almost atomic level dispersion has been achieved, okay, so that your particles are small. It is what we call it normally is decorated, okay, wherever you want a distance of few angstrom, it can be placed, and that's how you can reduce the amount of platinum. So I think this is just a few days back I copied. In fact, 93% of Indian exposed to the high level of particulate matter, less than 2.5 micron. And diesel vehicle are one of the sources. That's not the only source, but it is one of the sources. And second thing, obviously the diesel vehicle is also toxic for obvious reason that the chemical composition is not so favorable, okay. So this is how it is formed. For automobile engineers, they understand that it is formed during the combustion processes and when it is traveling in the exhaust system. There are two things happens. One is it grows in size, which is good, okay, because our sort of respiratory system can trap it. But what is bad is some of the hydrocarbons gets condensed, and that's provide the toxicity, okay. So this is the device called diesel particulate filter, which is the most efficient device, okay. So it has got a honeycomb, you can possibly see. Just a minute, use a pointer. So this is a honeycomb, but alternate channels are plugged. So if your exhaust is coming like this, it cannot go like this. It has to pass through these ceramic walls or the ceramic membrane. And the particulate matters, the soot particles gets trapped there. And this offers you about 95% efficiency and it's available commercially. The challenge is, why don't we just get this device and fix it in our diesel vehicle and get rid of 95% of this thing? After some times, the soot will clog this filter and the back pressure will be high and finally the engine will stop. So cleaning of this or regeneration of DPF is a challenge because it burns at about 550 to 600 degrees Celsius, while the diesel exhaust temperature is about 200 degrees Celsius. So regenerating this in an energy efficient way is a challenge, okay? And catalyst can obviously work for this. Catalyst normally reduces the temperature of the process, okay? So there are many catalysts which are mostly noble metal based, and they work on a reaction of nitrogen oxide to nitrogen dioxide oxidation. On this, NO2 reacts very quickly with the soot to form CO2, and that's how your DPF gets regenerated. We are working on a non-noble metal based catalyst, okay? So we work mostly on the perovskite and the mixed metal oxide catalyst, and this is from one of my mentor and a very good collaborator, Professor Teroka. Okay, he worked and he rather started this domain of multiple applications of perovskites. Okay, so because of short of time, I cannot go in much of the details, but these are some of the compositions he identified by himself and through the literature, which can work quite effectively as far as these reactions are concerned. Perovskites are it's kind of a mix of sites. All of us know the synthesis temperature is generally quite high, and that's the reason these are the sintered faces. And because of the sintered faces, you have a very low surface area. That's the challenge with the perovskite. While in the commercial catalytic converter or DPF, we use alumina, high surface area alumina. On that, we disperse the platinum. In this case, the perovskite particles are large, so they're not suitable for the dispersion of alumina. So you need to try multiple synthesis processes to prepare the supported perovskite or to prepare the, like the low temperature synthesis. So we have worked a lot on this area, and we tried many synthesis sort of processes so that we get the perovskite phase at lower temperature and we can possibly achieve a higher surface area. Okay. And then this is one of the catalysts we found is very interesting, which is giving a high catalytic activity, strontium ferrite. We have done the simple synthesis followed by a typical characterizations. I'm not going to go in the details because of paucity of time. And then we have done the catalytic evaluation of this catalyst along with this. But fortunately, we are fortunate to have a 3 level of catalytic, not needy in fact, but we have access to one of some of our very good collaborators. The first level is a fixed bed small lab reactor or thermogrammetric, using thermogrammetric technique. The second is a batch scale facility, okay, using a small diesel engine. And third, you can prepare the full scale prototype and test it on an engine dynamometer, which is also as per the regulatory protocol. So this is again the fixed bed catalytic reactor where we have a mass flow controller, we have 2 reactors. The heater is controlled like normally ATS furnaces, and it can be fed to the NOx analyzer and the GC. And then the whole thing is SCADA based, so you can control the reaction. After evaluating multiple catalysts in the laboratory, the next level is we prepare about 100 cc or 150 cc of support coated with the catalyst. And I use a facility of Kyushu University wherein they have a small diesel engine kept here. And the exhaust line is diverted, okay? And here is your catalyst coated support is kept. And then you can control the temperature and the airflow. And obviously the soot leaden, exhaust is trapped here and it is catalyzed and heated and it will generate CO2, which you can measure using this, analyzers. And also you can check the back pressure. That's the second next level of evaluation, which we shortlist about 3 to 4 catalysts and we go for this. We also try to perform some in situ or operando studies to work on the mechanistics aspects. In fact, one of my intention to show this slide to especially students who normally complain about the space, that the Japanese labs probably have the minimum space. But this is how they arrange the things and they ensure that there is no accident. Okay, so we should, I would say that we should encourage our students to realize what we have and worth of it rather than complaining that what we do not have. And of course, the Japan has multiple problems of earthquake and all that, so they have to take care of everything. So this is like the results we got to explain you quickly and to make it less complicated. This is the synthetic soot, which is a standard soot, which is combusting at about 550 degrees Celsius. Once you mix it with the catalyst, it is getting combusted at about 375. So from 550, your combustion temperature is coming down to 375, which is still high. Okay, you need to get it, say, around 300 degrees Celsius. But in 1 or 2 catalysts we got, so we published a lot on this domain, so you can check with our publications. And this is another way of expressing it. This is a CO2 formation through oxidation of soot. So you can see around, it starts around 350 or 375, it is significant. And then it is coming down. Why it is coming down? Because it's a batch reaction in which we have used a certain amount of soot and the soot got exhausted. Then we select the catalyst based on the pilot study, I would say bench scale studies, and we prepare the full scale prototype. Simple dip coating method, but sometimes it is complicated because the reactants react with the support. And then we use 2-3 facilities. One, frequently we use Professor Avinash Agarwal's facility at IIT Kanpur, who has got almost 10 engine dynamometer, who is one of the best in IC engines, I would say, in the country, and one of the best in the world as well. And they got a very good emission analyzers. There we generated data on our non-noble metal-based catalyst. And to quickly explain you, the CO was oxidized at about 200 to 300 degrees Celsius, hydrocarbons also, and so is the particulate matter. Okay, this is without catalyst and this is without device. So the PM or soot contained was also reduced using these full-scale devices called DOC. But long way to go. Okay, because this is just the first step. Then you need to subject it to different capacity of engine. Then you need to also subject it to different load RPM conditions, which we have done partially. But the most important is the durability protocol and the temperature requirement. So recently, we have also prepared some prototype of DOC and DPF for retrofitment applications in genset, because there are CPCB norms for old genset to be retrofitted, and it's a relatively easy application. So we have prepared this and then we have tested at CSR IIP Dehradun. Okay, and fortunately this is also showing very good result. But as I mentioned before, it's level 1. The next level will be on a higher capacity engine, and then the third level will be durability protocol. Only then we can claim that this device can be commercially useful. But I'm happy that we are not restricting our work to the lab level and not actually going for the next level of prototype preparation, because that gives us a fairly good amount of not only confidence, but whenever we think about a new catalyst, we think about prototype preparation. Okay, so these are some of the interesting engine results. I think I'm already exceeding my time, which I normally don't want to. So these are the results of our DOC. Okay, yes. So finally, in the summary, I would say that environmental challenges have been there since ages. It's getting severe. Okay, there are new pollutants. We call it emerging pollutants, not only air pollutants, but the water pollutants also. As I mentioned before, there is no assimilative capacity left in many cases, especially in case of air pollution. Okay, our atmosphere and our nature is absolutely full. It cannot treat by itself. While energy demand will increase for obvious reason, because we are growing, we must reduce the footprint, okay, of energy mix. What is energy mix? For next 20 years or 30 years, we can't only depend on the solar or the biomass or nuclear. There'll be an energy mix. So we need to work on that. Much innovations are possible in carbon capture, utilization, and sequestration, and material development is one of the keys, I would say. So there is a renewed interest in the low-cost catalyst, low-cost materials, okay, or for many, many applications to come. So in addition to very conventional criteria of, we used to call it activity, selectivity, stability, and at the most cost per catalyst, we should look into the life cycle assessment point of view as well. But the positive thing is with the much better understanding of structure property relationship and mechanistics aspects, I can see a lot of literature of very interesting developments in this domain. So I'll stop here. This is the team who is actually responsible, and they should enjoy the credit along with some of the collaborators. Thank you so much for Shetty Madam and the organizers for this opportunity. And I'll be happy to take questions if you have. I can see a question, what are the future aspects of electric vehicles? Okay, I'm not an expert in this area, but you know, like there is a very good possibility of introducing electric vehicle, which we are doing aggressively, barring few accidents, all these things which are always there and which can be taken care. What will be very important for us to green our electricity? Okay, if majority of our electricity for EV application is coming through renewable sources, then your overall footprint will be less. Okay, and if it is coming from, say, coal-based power plant, then there are different aspects of it. There is recent publications from IIT Bombay, and there is also from Professor Avinash Agarwal's group and from IIT Kanpur, wherein they're trying to say that EV is not that easy. We need to take care of certain aspects, including what kind of a power generation you have to power the EV. Okay, otherwise your footprint will be significant, because we all understand that if you have a two-step process, naturally you lose efficiency. But EV also has a couple of other advantages. One is, if you have a power plant, the power plant normally have a 2-3 stacks, okay, or chimneys, and the emission from 3 chimneys can be controlled more easily rather than 500,000 of vehicle which are fed with this electricity. Okay, because these vehicles are moving around your exposure zone, they are inside the city. Okay, so that's why the exposure of emissions are less, obviously, in the EV. Okay, then there is no sound pollution and all these things. So there are advantages for sure. Okay, and we have to go for it because in any case, we are trying to reduce our carbon footprint of energy generation.
Any more questions? Anyone? It is my privilege to propose the vote of thanks for this session. I, on behalf of KJ Somaiya College of Science and Commerce and the entire fraternity, extend very hearty gratitude to our speaker for his for enlightening us with the importance of sustainable development and various materials and processes for cleaner energy and environmental applications. I am sure that the participants are benefited by this wonderful session. Thank you so much.
Thank you so much for the kind words. So I'll take leave. Thanks.
Good afternoon, everyone. Welcome to the next session. I, Saili Lokhande, is super excited to introduce our speaker for today's event, Dr. Ganesh Naik, Director and Professor of Chemistry and Environmental Sustainability Program at St. Mary College, Omaha, USA. He received his BSc and MSc from KJ Somaiya College of Science and Commerce and his PhD from the Bhabha Atomic Research Center. He did his postdoctoral studies at Duquesne University and worked as a visiting faculty at the University of Pittsburgh in USA. His research interest lies in the areas of chemical and climate change education with a focus on curriculum development. He is also engaging undergraduate students in hands-on experiential learning projects. Today, he will be sharing his expert opinion on sustainability by integrating United Nations SDGs into chemistry curriculum. So I welcome Dr. Ganesh Naik, sir, and I request him to start the session.
Thank you. Now? Is it
Yes,
okay?
yes.
Is it better?
So,
Sorry.
yeah, so I'll change the slides.
Okay, I cannot change slides. It seems we mastered the virtual technology, so in person we are taking a back step. So. So in this presentation, first I will give the overview of sustainability. And then I will see where does chemical education and sustainability intersect. And then I will give some examples like how we can create a bridge between sustainability and chemistry curriculum. So let me start giving my thought on sustainability. So can you go to the next slide. Yes, so this is one of the approach we used after Industrial Revolution. So after Industrial Revolution, what we did is we kept humans in the center of development, and we thought planet Earth, all other life forms, natural resources, and the ecosystems, they all are the, what do we call, resources for human development. So we always, we developed a society which is human centric. But in last 20-30 years, we realized this model of keeping humans in the center and keeping the rest of the things around it is not sustainable. So what we realize is we have one Earth, and humans are also one of the component of the whole ecosystem. So it's like we, other species, natural resource, all this forms different component of the Earth system, and we cannot, if we live the way we are living, we cannot live a life, and our future generation will not have the natural resources or the ecosystem to sustain themselves. And to give an example, simple example, like 50 years back, if you ask your grandma, like, would you go and buy water? She will laugh. She will say that I will not buy water. Why? It's free, correct? But I don't think that is true now. Like, and thanks to COVID, it also showed us the second precious resource, which is air, correct, is also not which can be commercialized. Like, means you can see that people were selling air canisters. So I think these are the essential commodities. This showed us that we cannot keep humans in the center. We need to keep the ecosystem and other aspects of the planet Earth in the center in order for the holistic development of human life. So can you move to the next slide? So now why we should not do that? Like, if you consider the humans, like if you go from like 1750, like, and once the Industrial Revolution started and development of newer medicines and newer technology, we have an exponential growth in human population. So like if you think about till 1900, the Earth's population was less than 1 billion. Now, if you see in like 120 years from it went to 1 billion, and it is like now close to 7.7 billion. And soon it will reach to like 8 to 10 billion. So I think it has an exponential 4 to 6-fold growth. And we cannot sustain that model of growth in human like numbers unless we manage our resources and the ecosystem, because that is that's the reason it's very important to understand we are part of the ecosystem. We are, and with that, at this rate, the nature itself will not allow us to sustain for a long period of time. So, can you proceed? So now coming back to our theme of this conference, like United Nations Sustainable Development Goals. Actually, this concept was floated in a conference in Brazil in 2012. So they said like, oh, we need to develop some kind of theme for sustainable developments for the different countries around the world. And initially, after brainstorming, they came up with 300 goals and they said like 300 goals is too many goals for people to remember and achieve. So then by 2015, they reduced that 300 goals condensed into 17 goals. So that's what we know it as 17 SDGs, or Sustainable Development Goals, developed by United Nations.
And soon after in the UN summit, many of the countries like adopted, like that's one of the benchmark. So this benchmark, we have to meet it by 2030. So what's this benchmark? This benchmark is about holistic development of humans in this planet Earth. So, and you could see in that 17 goals, which are the indicators of this holistic development. Can you go to the next slide, please? So if you see this 17 goals, like if you consider from no poverty, zero hunger, good health and well-being. So if you see all these aspects, so they are not one aspect, they are aspects of a complete aspects of a human being, correct? So we need to consider humans. So that way they consider it's not just like an one or two indicators. So they did a very good job in merging all these things. It took and creating this 17 objectives for humanity for next, I think we are in 2022. So it's like next 8 years to achieve some, at least if not all of it, some part of it. So can we go to the next slide, please? So this is one of the things I would like to highlight, and actually because this is based on the SDGs. So when we talk about poverty, so suppose if you ask any person, what is a poverty, correct? So the first thing which comes to mind is the person doesn't have any money, correct? If the money is not there, then that means he or she is a poor person. But actually this SDGs and this understanding says, and Amrita Sen has the Nobel Prize winning economist also said, poverty is not just lack of money, it's not having the capability to realize one's full potential as a human being. So if any system or if any society, it will not allow one person to develop to its full potential, then that is also a form of poverty. It's not just not having the money. For example, if you can consider quality education, correct? So if you see in India, there is only few percentage of the people, they get into the admission into the institutions where they get all the resources. But I think 90% of the students, they do not have that opportunity. So if that whole people struggle to get into that kind of form of education. So access to quality education is also a form of poverty. It's not just the money, correct? Like if you think of it. So, or if you consider justice system, like when we have this the interesting incident from the recent events, what happened during COVID. So one of the manufacturer of COVID vaccine, when he started vaccinating the country, he started getting the call from influential people and suggesting that they should get the doses of that vaccine first and then ignore the common population. So that means we don't have a strong institutions which will give justice for all, correct? So those kind of systems also kind of poverty. So poverty is not just about money, it's about building peaceful, strong institutions which can keep the justice. So we also all know that, correct? We had a very interesting talk since morning about affordable clean energy, water system and sanitation system, correct? So these all are the different indicators. If people don't have that access to those indicators, that means they are poor. So we cannot say that I have like maybe an 1 crore in my bank but when I'm traveling, I'm inhaling a polluted air. That means I'm poor because I have a poor environment which I inherited, correct? So money doesn't solve all the problems. So it's not about poverty. It's not just the money aspect. It's the holistic development of humans. So I thought first I will give you the concept of sustainability in a way that we understand what sustainability is. Sustainability is nothing but holistic development of human beings in the ecosystem as a species. Not so now that first segment is done. Now I want to bring the aspect of chemistry because that's what the second aspect of the thing, correct? So now how chemistry can help to achieve these goals, any of these goals of sustainable development, which is like 17 goals created by UN. So I'll give you an example. For a normal person, correct? For a normal person, they are like, if you are not a chemist, like fortunately, all of you are from chemistry background. I think same thing for the people who are attending from the audience also. They have some kind of interest or expertise in chemistry. So for a normal person, they will say that, oh, this is a t-shirt, correct? So this is a t-shirt which I'm buying. But think, if you're a chemist, if you are a chemistry student, for you, it's not just a t-shirt which you're buying for 200. You'll be thinking, oh, what that t-shirt is made up of. Oh, it is made up of cotton. So if it is made up of cotton, what cotton is made up of? Okay, cotton is made up of cellulose. Then you will say that, oh, if cotton is made up of cellulose, what cellulose is made up of? Glucose. So you think at a molecular level. So means you look at the same material, same word, but in a much more deeper lens. You look at the same things that what ordinary person looks, but you ask the deeper questions. So you will ask this question that, okay, if it is made up of cotton, how much water is used to grow that t-shirt? How many dyes were used to color that t-shirts? What kind of pesticides are used while growing the cotton, correct? So all that footprint, environmental footprint, as the previous speaker mentioned, correct, is you will consider all that footprint, and then you will think the next question, fundamentally, is it really the t-shirt which you are buying for like $200 to $500? Is it a $200 t-shirt? Like, if it's not a $200 t-shirt or 200 rupees t-shirt or 500 rupees t-shirt, what is the actual cost of that, correct? What's the actual cost of that? What's the environmental footprint of that things? That you will ask that question. So one of the advantage of all of you or all of us being a chemist is going into the depth of the everyday things around us, because chemistry is there in everything, correct? So going into depth and asking these fundamental questions in our learning, correct? Can you go to the next slide? So now other benefits of, now let me talk about from education point of view, correct? Since morning, I think we had a very interesting talk on research aspect of sustainable developments. But now let's talk into the educational aspect of development. So most of the time we have seen that the educational aspect actually, when I'm growing up, maybe definitely things have changed now. When growing up, like we focused more on memorizing the answers or given a question and we have a set of answers that we need to know. And then we need to memorize the answer and lay out the process. For example, okay, how lanthanum is extracted from its ore. Like you learn 20-step process and then try to write it in the exam and you mastered, you get the score, correct? But now here I want to bring a different perspective, like because as an educator I'm spending, so we are living in an era where we have an incredible amount of collective knowledge that is in the form of internet, correct? So because we don't have to memorize each and every step. If you want to know any answer, correct, any steps, you can look it up. You can look it up online. So it's like when I was attending a conference, it was amazing that one of the speakers said he was working for NASA, and he said the computing power of the overall scientists of NASA was less than the computing power of one person is having in their hand now. And with that computing power, they were able to send a person into the moon in 1960s. So that means the computing power, with that less computing power, they were able to send a person from Earth to moon. And right now in your hand, you have more computing power than the whole NASA team had back in the time. So now when we think we have that much computing power, that much knowledge in our hand, do we really need, that is our second brain. I always believe like our mobile phones and our internet is our second brain. So do we really need to memorize each and everything? We don't have to memorize each and everything. But what we need to do, we need to ask that, develop that curiosity, develop the questions with that, the curious minds, correct? So where we can, and students and engage students. And I will give you some examples because this is a philosophical point of view, but I will specify with some examples later in my presentations. So the benefit of integrating chemistry into sustainability into chemistry curriculum is, generally I have one of the questions generally students says when they are learning at a molecular level, they said, where is the application? Why I'm learning this? What's the benefit of this? So, but when you integrate this sustainability principles or problem solving approach, you will always talk from that application point of it. But at the same time, make sure that your foundation in the molecular aspect of the chemistry is very, very clear, correct? So you try to bridge that, like the application as well as the molecular world. So then you see that, okay, this I am molecule, so I'm studying, or this element I'm studying, but this can be applied in this way. So that's what our researchers presented since morning. So can we go to the next slide? So I will give you an example now. So after saying that what is chemical education and what is sustainability, let's discuss some practical examples where we can say how this can be integrated, like correct, into chemistry and sustainability can be integrated. So this is a traditional periodic table I learned when I was growing up, where I have to remember each group one is alkali metals, group two is alkaline earth metals, and all the different physical and chemical properties of these elements. And I think this is our Bible for what do we call all the chemistry students. I don't think any chemistry students can say that I'm a graduate without knowing the periodic table, correct? So this is a traditional approach. I'm just giving a thought, correct? It's a, whenever we do this seminar or when we do this gathering, it's just a thought experiment. So I just want to bring a different perspective. So can you go to the next slide? So instead of presenting a chemical periodic table with that approach, which is a traditional approach, know your alkali metals, know your halogens. Now let's look into the periodic table, which was developed by Royal Chemical Society, and look into this and see the color coding. This color coding is very different from the color coding of the previous one. So in this, they talk about, if you see the elements which are in the red, correct? So that means these elements we may not have in next 50 to by 2100. So this is like, although we have developed significant technologies based on these elements, but these elements will not be easily or economically available to us to develop the materials. So now you ask a student. So like, let's assume if I will ask a students this question, who learned their periodic table and other things, correct? Now tell me indium, correct? Let's look into indium. Why we have to care about indium? What's the benefit of having indium in the why it is in the red? Does it really we should be worried about it? Now students have their computing power in their hand. Let them research, let them go beyond the traditional textbook and find out why indium is important, correct? What's the role of indium? Why we are talking about indium as one of the red color coded. So now, just to give you an answer, because this is a presentation, not a class. If it's a class, then I will give you that question, correct? But since it's a presentation, I'll give you the answer. The indium is there in all of our hand. It's part of our everyday technology. Like whatever touch screen you are using, the touch screen capability is not possible if you don't have an indium oxide in your screen, because that has a great optical and electrical property. That's the reason you are able to use the touch screen. So think about it. All majority of us who evolved into now from regular traditional phone into smartphone. So we are using smartphone or any touch screen capability anywhere you are going, and one of the most critical elements which is used in the touch screen feature is the indium component, has the indium component. So now think about this part. So now if we are not able to develop an alternative material, or if we don't have that, then what happens to our technology, correct? It will suffer, or it will become too expensive, like as in the beginning. So that kind of now, so now the question is students can find out, okay, what are the alternative possible, whatever possible, what are the options we have if India we ran out, correct? What are the other elements from the transition elements we can look into? This is the creative way of asking the same questions, correct? You are learning about the periodic table. They know indium is a transition metal and I'm looking into some other transition metals. But what are the ways what I can find out? Now, why indium is so, what happens if we ran out of the indium? Can we recycle indium effectively? What are the challenges, correct? So that process they can, so we are making students to think about the problems which will happen in next 20 years rather than memorizing the process which was developed 100 years back. Are you see the shift in the thought process in the curriculum development? So in the curriculum development, we are not trying to memorize the process. Aluminium was extracted by Hall's process, correct? So I don't want, that was done in 1850 and that changed the humanity. Aluminium was one of the expensive metal. Because of efficient extraction, it became economically viable. Okay, that's really great. But is it a challenge for 21st century? No, the challenge for 21st century is
See, this screen share is still.
Hello, hello. Voice आ रहा है? इसका आ रहा है? Voice आ रहा है? So you can continue. So yeah, it's okay. You can continue from there. Zoom पे क्या दिख रहा है? Zoom पे screen share. क्योंकि screen share
I think, can you hear me?
Yeah. Yes, yes.
Should I do full screen? Yes.
cover.
This one?
इसका अटैच करो। हाँ करता था 1-2 मिनट। So you can continue. Connect it. Connect it. You are visible on that. You are visible on Zoom.
Okay, so when we talk about this, you can hear me, correct? Yes. So if you have to give the other example, correct, like other than indium, like so this, I think we had an interesting lecture from Dr. A.K. Tyagi from Bhabha Atomic Research Center when he mentioned about going from lithium to some lithium and rare earth combination, but at the same time he mentioned about sodium. So now we can ask this question to the students. So now if you think about lithium, sodium, they are both are alkali metals, correct? So both have like definitely why, and if you consider sodium, sodium is not as rare as lithium because we know that sodium can be present in the form of sodium chloride. So why we can't go into the process where we can use this sodium as an alternative element in the battery development process, correct? So there were like, definitely there were some energy density and charge cycle issues, but can that be addressed? Because if you see the properties, the physical properties and chemical properties, they are very close relatives of each other, correct? So, but the scarcity of lithium, what we are facing, we will not have that. So these kind of questions can be asked from the periodic table. Or when we look into this elements like phosphorus. Phosphorus is a very interesting element, like when we think about this agriculture, correct? So there is a sustainability deals with agriculture. So in agriculture, the three elements which are very critical in food production is nitrogen, phosphorus, and potassium, correct? That is called NPK values. So now one of the thing is if Royal Chemical Society has put this phosphorus as one of the yellow category, that means this is one of the elements we may not have easy access to. Now if you ask this question, why phosphorus? Because phosphorus can be easily available to us through one of the easiest process which we do, like through sewage, correct? If the sewage is an easier process by which phosphorus can be easily available, why we can't make phosphorus and our sewage, correct, combination in a way that we can have solve the problem with these elements, because nitrogen and phosphorus are clearly like the most abundant element in our sewage system. So these kind of questions about elements, correct, and their properties in our everyday applications, which can be in electronics or it can be in agriculture or battery technology, can be asked as a thought exercise to the students when they learn little bit of periodic table. So rather than having when they are asking questions, so these kind of creative questions which involve some kind of what do we call research, where they can find the recent articles, recent developments, and try to see that if it is possible or not, correct? So that way, what happens is it will give them the idea about 21st century problems or 20 solutions for the problems in the 21st century, rather than memorizing the process of developed in 19th and 20th century. So that's what I want to bring. I want to bring a perspective in curriculum development. Our emphasis should be on 21st century issues rather than 19th and 20th century issues, because we still teach gas laws like Boyle's law, Charles' law, and those things. But people, when you ask them about, tell me the three most what do you call it, greenhouse gases, everybody will know carbon dioxide, but then after next two, they will not able to what do we call answer. And if somebody says water is also a greenhouse gases, so then yes, water is a greenhouse gas, but then people will challenge that, correct? So, but why water is not a greenhouse gas as compared to carbon dioxide? So if you think about why water is not a greenhouse gas, because it's a thought question, correct? Because if you think about why water is not a greenhouse gas as compared to CO2, CO2 has a longer life in the environment. Water can be easily cycled back through water cycle when we get rain. So that's the reason, although water has a higher heat absorbing capacity, we don't consider it as an greenhouse gas. So means what I'm saying is we can teach the same gas chemistry, but in a very in a way that where we can talk about the modern problems, like we can bring them aware about, okay, these are the issues which you are learning about gases, correct? Rather than solve ideal gas equations and Van der Waals equation of state and something. They should definitely know. It's like it should not be compromised, but at the same time it should be 60-40 or something, like not 100% on emphasis on those principles which you learned back in the century. So now this is one of the things which can be a case study questions. You can say talk about electronics, correct? So when we talk about electronics, you can ask this question. So okay, tell me if you have a high-end smartphone, like how many elements from the periodic table you have in the smartphone itself, correct? Like if you consider it will somewhere range from 45 to 70. So from 40 to 75 elements from the periodic table you can see in that your smartphone which you are holding, correct? So now what happens to that smartphone? Like we are like more than like out of 7.2 or 7.5 billion people, if you consider half the population are using some kind of phone, like correct, or let me conservative, 1/4 of the population, so at least 1.52 billion phones are there, correct? So what happens to those phones, electronic gadgets and other things? They end up in most of the poor countries where people use this not only as a garbage, but then coming back to my original thought on holistic development, is it possible for these people, they may earn a little bit of money by extracting some metal, correct? But is it possible that they will have a clean water, they will have a clean air, they will have a good health when they are living in that kind of heavy metal polluted environment? It's not possible, correct? So it's not, we cannot say that we are getting rid of poverty by dumping our used electronics into the poorer countries, which earlier it used to be India, but now India is developing. So many of the African countries, they take the world's electronics and other things. So we cannot say that we are helping them by giving them our garbage, correct? Because we are not helping them with their SDGs, like overall development. So these kind of thoughts, these kind of questions, correct? So then you can say that, okay, now if that's the case study, now tell me how many elements in the periodic table elements are linked to SDGs, especially with respect to electronic recycling. So what can be recycled, what cannot be recycled? So that kind of questions can be asked in the chemistry classes, correct? So now what are the, like people say that I do electronic recycling. Like now when we talk about electronic recycling, especially in India also, there is a lot of recycling mechanism happens through like informal sector, what we call as, but when these informal sectors are done, they are not trained enough to take care of the water bodies. They are not trained enough to take care of the, what do you call, heavy metals and all those things. So it in turn affect their quality of life as well as the quality of life who are living in the surrounding. So now, so that's the reason it's very important that people need to follow some kind of guidelines where these kind of effective recycling can be done in a very effective way. And this is one of the events which I do in my campus back in the US. Actually, I started in 2009, and so we do the electronic recycling event and then have people bring every year, like it's an annual event where people bring their electronics, and then we have a certified electronic recyclers who will collect those things, and then we get the tracking of what happens to those electronics once it is recycled. So there are that, I think, as a campus, because I think I visited this Christ University in Bangalore. They have a Center for Social Action. This is one of the things chemistry students can organize, like, okay, we want to do social actions, but one of the thing is there are two products which are widely used, but they are not properly recycled. One is electronics and other one is pharmaceuticals. So can we create those two things and proper recycling mechanism, find out those who are the vendors who are doing that, and can we collaborate and create this kind of closed loop system, and then try to educate ourselves what happens to the electronics, what will happen, all that processes, correct? So this is one of the things which you all can take out, correct? If you are a PhD students, you can think about, okay, what are the ways by which electronics are recycled? What are the potential, opportunities for what kind of metals we can extract efficiently? So there are a lot of things you can do if you take this process in a much more formal way. So now, this is one of the things, correct, which I had the question for Dr. Tyagi, because he talked about smart batteries using rare earth metals. But if you see the data on rare earth metals, it's heavily, and that's one of the reasons also China is able to produce electronics in a much cost-effective way, and none of the countries in the world cannot compete with China with respect to electronic production, is because they have the high reserves of rare earth metals, and so it's a geopolitical issue. So, so if you see the amount of rare earth metals are extracted and used by different countries, if you see China leads the way by far, like none of the other countries comes closer to that also, because they have a higher resource of those rare earth metals. So in 21st century, this is one of the geopolitical things if it comes, correct? How other countries who want to use those technology, how are there, do we have any alternatives? Do we have any alternatives for rare earth metals? So those things, correct? Those things we need to learn, correct? So when you're learning about lanthanide chemistry or actinide chemistry, many of those elements are made, like some of the elements are made in the lab, correct? So some of the elements are like used in magnets and so many electronic industries. So how we can effectively minimize or find the alternative for those rare earths rather than developing new technology. We know that these materials are already, we don't have enough material. So why we want to put a lot of research and effort, money into something where we are not 100% sure about it. So correct. So that thought should go into the material development process, which in turn thought should go into the curriculum development process to ask that question. So when students are asking that questions, so then what happens is they will not get into the research on that field. They will go into the proactive research rather than reactive research. So another example, correct? So the previous examples were all about the elements from the periodic table. I want to give a second example about combustion reaction. So now this is one of the thing which is like CO2, which is a widely talked about element. Like, so when we looked into CO2, like for last like 800,000 years, correct? The CO2 levels were below 280 parts per million. This is one of the concentration problems we can ask to the students, correct? So now tell me, CO2 is in 280 parts per million. So why we use parts per million, not molarity, not normality? Because it depends upon the whatever unit what we use is for remembering the measurement. So if you express in some percentage solution or some molarity, the number becomes too odd to remember. Now if I say that 280 parts per million, it is easy to remember. But if you see as I said, like coming back to my previous slide, when we were in 1900, our world population was around 1.5 billion. And at that time, CO2 was also around 280 parts per million. Like it was, but now if you see, CO2 has gone up 410 parts per, so now recent thing was like 420 parts per million. So that means we have, for the last 800,000 years, we never had that CO2 level of that level, correct? So now with that level of CO2, which is increasing like from 280 to almost 420, is it possible that we can keep the climate, I would not say climate cycles, correct, conducive for human developments? We will have very unpredictability in our weather pattern. It's not about, people misunderstand when we think about global warming, or it's like warming or cooling, correct? But the question is not about that. It's understanding the climate pattern. Like the change in the climate pattern is what? 1 year you will have a lot of rain, and the next year you will have a severe drought, correct? So this change in the weather pattern will happen when there is when there is a greenhouse effect will happen, correct? Because so those things students need to understand. So now the question, see, now let's go into the chemistry aspect of it. So this is the environmental aspect. As a chemistry student, now how do we know? How do we know that people have for last 800,000 years, we had 280 parts per million or less carbon dioxide. So now where does the chemistry comes into picture? Now, if you see into this molecule, correct, the phytane. Phytane molecule is one of the things which is used to do the dating of this carbon dioxide. Now, how phytane is used to do the dating? That question you can ask to the students. So they have to read the article and they have to find out how phytane, this molecule, is used in determining the CO2 level for 800,000 years. Like how this data is compared to the what was the previous data they used to use. This was published like 3 years back. So now what was that? They used to use Arctic core data. So now what's the comparison of Arctic core data and how that is different from this phytane chemistry data, correct? So here the concept of carbon-12, carbon-13 isotopes and all those things comes into picture. So all that thing, what happens? What you are learning? You are learning the application, you are researching, you are using the computing power of your phone, and you are trying to understand the chemistry and sustainability together. So it requires just the questions, right type of questions. If we ask, then we will able to what do we call try to spark students interest into chemistry, and at the same time we will make them intellectuals, correct? So one of the this is one of the thing which when I got to know, I was really amazed, and I don't know that it's the right answer or not. Have you seen this more? Many of the industries, correct? Like whenever we think of combustion reaction, many of the industries has these kind of chimneys. Like that was a very common form of development in human society. It's because our scientific knowledge was primitive. So people were thinking, like that's what I heard. So people were thinking, if you put it like a tall chimney and then let it into the atmosphere, then we don't have any problem. But then we know that, correct? It's not true. Correct? That problem is precipitating in terms of acid rain. It is coming in the form of smog. So the concept was build a tall chimney and then that just goes away out of sight. Correct? But it's not true. Correct? So knowing that true science, correct, it will help us to understand how we can solve these kind of issues, which people will not. It's a design problem. Correct? We think now people are talking about, okay, now that doesn't go away, that comes back. Now we are talking about, you heard the research presentation, how we can effectively do carbon capturing, how we can do the source reduction. So those things became part of it but when they were designing after industrial revolution, that was not their thought. They didn't have that thought at that time. So now this is one of the things related to combustion engine, correct? Like so previously they used to add lead, tetraethyl lead as an into the fuel. So now why lead was added into the fuel? Because fuel, when it burns, it needs smooth burning, correct? So you need an knocking agent, which will help in smooth combustion of that fuel. So people use that for like almost like since the invention of the fuel, like 1869, correct? And interestingly, the first place, correct, where the oil well was drilled, that was the place where I worked as a visiting faculty. So that's the time when I heard that presentation, Titusville. That's where I lived for a year after my postdoc. And now that whole town is like a ghost town because the oil is gone, the town is shrinking, correct? But that's the town I lived in 2006. So coming back to that, so since the oil was discovered, they were using this lead-based agent in order for it to burn smoothly. But then they realized that, okay, lead is like really has a lot of health and environmental impact. So then let's change it to, in 1930s or 40s, I think they changed from lead and to methyl tert butyl ether. So they changed it from lead to the methyl tert butyl ether. And then when they use that, they realized that, okay, now we found that we removed the lead, now we are using an alternative agent. But now that problem is, they found out that this is a very stable compound in water bodies. It doesn't go away. So now it leached into all the water bodies, and water bodies are contaminated with MTB. So then at that time, when they were trying to do that, this continued for next 50 years. So are you understanding the like scientific challenges, correct? We design something, we design a solution, but we don't know the whole answer. But the beauty of science is we try to go to the next unknown and try to see how we can solve that problem. So now, if you see, like people say that, oh, we are adding ethanol to the fuel. So have you, did you get the background, like why ethanol came into picture? It came from tetraethyl lead to MTBE to now ethanol. So it's doing the same properties. But now there is one more story to it, correct? Like people want to make that as a fuel. Okay, ethanol is a fuel, like you heard the morning presentation, correct? Ethanol is not good for the fuel. It can be used for fine chemicals, but it cannot be used for fuel because the energy cost of producing ethanol itself is very high. So it can be a good 2% solution, which will be helping with the engine, with like what other things did, but it cannot be a substitute for fuel. So those kind of awareness if students have when they become the intellectuals, when they take positions, professional positions. So with that clarity, they will approach the problems, correct? So otherwise, they will what they will do? They will do a PhD in like let's say how I can convert a biomass into ethanol for fuel. But I feel they have used 5 years of their prestigious like life, correct, and the cream, the peak of their life into solving some problem which was not necessary to be solved. So I think it's very, very important that our young minds, bright minds, correct, we need to give them enough understanding that when they try to pick the problem, they will pick the problem which are definitely we need to solve in 21st century rather than like picking a wrong problem and spending there like, because when you are like 18 to 30, that is your prime of your life where your brain is developing, you can contribute a lot, correct? So then you will pick the right problem if you know if you have the right understanding, correct? So that's where all this knowledge and all this curriculum changes plays an important role, like in creating a spark in students' mind. So this is one of the, how much time I can go because there are a few more slides I can go, 10, 15 minutes, 10 minutes. 10 minutes I can go, correct? So this is one of the things, correct? So when we talk about electricity usage, correct? This is one simple solution people should be aware of, correct? So now this is one of the, like this I took it from the newspaper article from I think Times of India or Economic Times. Like this is what the electricity demand for Maharashtra, correct? Like if you see, they were comparing during COVID period, how it has changed. So now, but one of the things is like, if you see there is so much fluctuation, but one of the things that I think hardly people talk about sustainability, talk about it, but it's very important. It's very, very important because we should always know that we need to understand peak electricity. Now, why we need to know the peak electricity? The reason is you cannot overnight design a system for that peak. You are getting it. You cannot design a system for the peak. So you have to build whole infrastructure for the peak hour electricity. So now let's assume the peak hour electricity is like 25,000 megawatt, correct? But you will not be using that 25,000 megawatt for the whole year, but you are using only during the peak hours. But you will have the infrastructure for the whole year. So do we need that kind of infrastructure? No. How do we can manage that peak hour? So it's like managing peak hour means what? Now this is the best example. This is summer months, correct? So don't do your washing laundries, don't do any electricity related things during daytime. When there is peak summer, you are using a lot of electricity. It's creating stress on the grid. So if people don't use that kind of, suppose if you reduce your electricity usage during peak hour, what happens? You do your laundry and other things during night time when there is no, sun is not shining, it's not like 35 degrees, it's like 28 degrees. So what happens? So we don't have to build that kind of infrastructure. So it's very, very important that our peak hour usage of the electricity we can reduce by just managing it diligently, correct? So whenever we don't need it, we don't have to use. There are a lot of chores which can be done in like ironing clothes. You should not iron clothes in a daytime because you are adding stress to the grid, correct? And then there are some rural areas. You are living in an urban areas, you will have your power, but rural areas will have a power sharing. So how do you manage that, correct? How do you manage that? By educating people about what is meant by peak hour, what is off peak, what is on peak, correct? So that way we can reduce a lot of what do we call electricity, building new power plants and increasing to meet that peak demand, correct? We need to have an average demand. So this is one of the other examples. Actually, I was fascinated to know this as a child. I used to go across this river, but I never realized it's a river because I felt like it's a drainage. So, like if you know, Mumbai has 4 rivers. I hardly anybody knows that Mumbai had 4 rivers. It's called Dahisar, Boisar, Oshiwara, and Mithi River. And the Mithi River was one of the, it was a sweet water river flowing through Mumbai, and nobody can now recognize that it's a beautiful sweet water river which flow through Mumbai for a long period of time. So that is one of the best example of what do we call of like we can talk, means like you can talk about this system. So we know that, correct? Whatever we had, we lost it now already, correct? So now coming back to that peak hour, one of the things which is air conditioning. Like I don't know, like what's the temperature of this room? 22, correct? So thank you. So the 22 is not the efficient way to run the air conditioning. Why? Now I'll tell you why, correct? Because the best efficiency of this air conditioning machine is at 25 degrees. 25.5 to be more accurate, or 26. So now you will say that why we need to learn, what's the advantage of what's the disadvantage of running at 22 versus 26? So now can you tell me, living in Mumbai, you all know that it's not the temperature that's the problem, it's the humidity, correct? Humidity is the biggest killer for in the summer months, because you sweat a lot. The reason is humidity is the biggest problem because water has now it's a chemistry thing, like I'm relating it to chemistry curriculum, correct? Water has a higher specific heat, correct? It is 4 times, it holds 4 times more heat than most of the metals do. So correct? So it has a higher specific heat. So now what happens? When you are using air conditioning as a dehumidifier means to remove that moisture. So what happens? You are reducing the heat. So when you are reducing the heat, that 26 also will become equally compatible that what you are having. So now it's a chemistry concept that I know that water has higher specific heat and I want to remove the water because it holds more heat. So that's what I'm using air conditioning for rather than cooling, correct? So if you are using it for cooling 22 degrees, you are going against thermodynamics, correct? So you have to use a lot of energy to bring that down the temperature. So you try this experiment. I do this in my home like for like last 10 years and I educate them, because it's like 26 is very, very comfortable temperature if you don't have humid air, correct? And you have seen that also, like in winter months also, correct? Like there is less humidity, and because less evaporation, less humidity, and you don't need that air conditioning. So, but experiment it, correct? So this is all chemistry and sustainability. I'm not so other thing actually you have seen like regarding this disinfectant, correct? Like which is used widely in COVID times, sodium hypochlorite, like you have seen this COVID time. So what's the chemistry of that, correct? Like what's the environmental impact of that? Because I'm running out of time. So like that kind of questions you can ask. Okay, like let me do this last 2 slides and then this one, correct? So this was one of the most interesting thing for me. Actually, I think till last 5 years, the focus was on like I think last 1950 to 2000. Actually, the focus was all on nutrition, the pyramid, food pyramid. Okay, take your carbohydrates, take your protein, take your fat. You should have more protein in your diet and all those things. So what we did, we tried to consume like a lot of food based on nutrition, and we created this food pyramid, food labeling and all those things, correct? Then what happened is, then we realized that all that food which you are trying to eat, the most nutritious food of no use, like that was last 20 years, correct? So last till 2000, that was the thing. Food pyramid was the goal for humanity, for food. But then they realized that food pyramid is of no use unless you have a good gut or good bacteria in your intestine. So then last 20 years, they realized that, okay, if you have probiotics, if you have a good gut bacteria, then only you will be able to metabolize all that food which you are eating. If your gut is not healthy or if your intestine is not healthy, then whatever food you are using, that is of no use, correct? So earlier food was our goal, but then we realized, no, we need to have a good bacteria also. But interestingly, last 5 years back, there was a Nobel Prize winning, they got the Nobel Prize, and this concept become very popular, is like autophagy. That what is autophagy? That means people do intermittent fasting. So you heard about intermittent fasting, correct? Now don't eat food. So have you seen like the focus is on from eating a lot of food, nutritious food. So now there is a focus on not to eat food, correct? So it's very interesting that how we evolve, how our knowledge evolves, and we try to adopt to that lifestyle and think that is the truth. But the beauty of science is science continues to evolve and our knowledge deepens, correct? So one of the thing is the amount of food which we are eating is always excess. You know, the very interesting thing. Why do we eat food? Why do we eat a lot of food? The reason we eat food because we are warm-bodied animals. So what happens is we are one of the species where we have to keep our body temperature, correct? Like 37 degrees Celsius. In order to keep that temperature, what happens is we have to keep on eating so that our body is, that's exactly the reason in summer months you don't feel like eating, correct? Why don't you feel like eating? Because outside temperature is enough to maintain your body temperature. So you don't feel like hungry, but in winter months you feel hungry because your body temperature has to be maintained when the outside temperature is low, correct? So, but one of the thing is food, like in combustion, in the fuel, the food itself is not an, very efficient process. So more food you eat, more you burn, you will have more oxidative stress, you will have more aging. So if you don't want to age faster, you have to eat less food because you are reducing the oxidative stress, correct? Because so it's so interesting, like, so why are we talking about food when it is not needed, correct? Like that much food. So this is one of the things which is when we talk about food production, we also think about the amount of food which we produce and the amount of food which we waste. And most importantly, do we need that much food so that we have to go and work out to burn that food? Because burning out food means you are again making it your body to age faster. You have a good muscles, but your bodies will age much faster, correct? If you have a limited, that's what autophagy paper is about. If you are not eating that much food, then what happens is your body is effectively recycling all the things and making it more effective system. So now to close this, actually, what's the solution now? Like, what's the final take? Correct? I always like to conclude now. So we learned chemistry, we learned sustainability. So what's the best thing we can do in 21st century? Like, I think best things in life are not the things that we need to understand. So we like to think that things gives us happiness, and happiness are not based on the material pleasure which we have. So as long, see this person, actually I really like to emulate him in my life one day, maybe few years down the line. He has only 47 possessions, which includes his bookmark also, book and bookmark also. So he has 4 t-shirts, 4 shorts. So think about the amount of clothing we have, and amount of clothing, actually, if you think about it. I think each person has maybe more than 10 pairs of shirt or something, correct? Or like, do we really need that? Do we really need that, correct? Like, so if you reduce the amount of clothing itself, correct? Like clothing itself, that will have a very great contribution you are doing to the humanity without doing any science, without doing any research. Because I don't think any person can wear 10 pair of clothes at a given time, correct? They just need maybe 1 or 2, or then they can manage with less than 5, 6, 7, or 10, or 15. I don't think people have more than 15, correct? So that, like that, there are a lot of things which we can realize that life can be life can be simple when we embrace minimalism, correct? So because then when we talk about the definition of sustainability, like meeting the needs of future generation, yes, then definitely we can produce offsprings and meet their needs. But at the current rate, I think our offsprings will blame their parents, and starting from, I think, grandparents, saying that why did you give us this planet and this life when it is not sustainable? Thank you.
Hello? Hello?
On behalf of Tejasomaya College of Science and Commerce, I would like to give a formal vote of thanks for this session. Thank you, Dr. Ganesh Naik, for this wonderful and informative lecture on sustainability. It will definitely be helpful in our future work. I am grateful to the organizing team, all the teachers, head of the department and principal of Tejasomaya College. And finally, I would like to thank all the participants. We look forward to such collaborations in the future. So this was the last session for today. We look forward for your presence again tomorrow at 9:30 a.m. Thank you. So all can leave the meeting room.
Tomorrow what?
9:30.